7 comets and the mystery of Atlas. Astronomers have just discovered something that should not be happening. Right now, 7 comets are heading towards the Sun, all set to arrive within days of each other in October of 2025. Never before has anything like this been recorded in human history. But here is what makes this discovery truly unsettling. Comet Atlas, an object from an entirely different star system, is also on a trajectory for its closest approach during this very same window of time. The probability of this is infinitesimally small, unless something is coordinating these arrivals. What if this is not a simple flyby, but the beginning of something far more profound? Tonight, we will investigate every possibility and speculate on the forces at play beyond our current scientific understanding. Stay with us until the end to discover what Atlas is truly doing to our solar system. Part 1. A sky full of visitors. In a typical year, we might see 1, perhaps 2 bright comets worth mentioning. Most years pass, with nothing more than a few faint smudges in a telescope that only the most dedicated comet hunters get excited about. But in 2025, it is as if the cosmos has decided to treat us to a parade. Let me introduce you to the cast of characters that made astronomers double-check their calculations. Atlas, Lemon, and Neat, 7 separate comets, each one carrying ice and rock from the farthest reaches of the solar system, all arriving within months of each other, like a cosmic reunion that no one had planned. Think of it this way. Imagine if 7 different friends from all over the country all appeared at your doorstep on the same weekend, each one claiming they had no idea the others were also coming. Possible? Absolutely. An absolute coincidence. Suspicious enough to make you wonder whether someone sent out invitations behind your back. Absolutely. This gathering creates what astronomers call the many comets clustering together in a relatively short period of time, observed from Earth's perspective. It looks almost orchestrated, almost as if something had herded them here. Before we delve deeper into this cosmic mystery, let us establish a few basic definitions. Perihelion, the comet's closest distance to the Sun, the moment when the Sun's heat transforms distant blocks of ice into spectacular trails of gas and dust. Closest approach. How close these objects come to Earth. This determines whether you need binoculars, a telescope, or just your naked eye to spot them. Brightness. The lower the number, the brighter the object. A magnitude of 6 is difficult to see with the naked eye under a dark sky, while a magnitude of 0 is comparable to the brightest stars. The visual evidence. The visual evidence is very compelling. Imagine a chart showing the appearances of typical, stretching across many decades, with dots scattered randomly over time, like raindrops on a sidewalk. Now, picture the year 2025. 7 dots clustered together as if someone dropped a handful of marbles. The pattern stands out immediately. Most years, amateur astronomers spend months searching for anything worth photographing. This year, they are spoiled for choice. Photography forums are buzzing, with images of multiple comet tails streaking across the same patch of sky. Social media is filled with time-lapse videos showing what looks like a coordinated celestial dance, the interstellar visitor. But this is where our investigation takes an interesting turn. Follow their predictable orbits. Something else was lurking in the interplanetary darkness. It was the 3rd interstellar object ever to be confirmed, detected in our solar system. Unlike our 7 resident comets, this visitor was not born here. It formed around another star, in another solar system, and it was passing through our neighborhood, on a hyperbolic orbit. This particular timing raised questions that kept astronomers awake at night. Was it a random coincidence of our solar system in recent would coincide with the visit of an interstellar visitor? Or could there be something more intentional at play? The investigative method throughout this inquiry, we will maintain a clear separation between events that are measurable and speculation. When we present orbital data, observation logs, and brightness measurements, You can trust in those numbers as we explore the possibilities that lie beyond confirmed science. We will clearly mark them with speculative tags. This is not about pushing theories. It is about following the evidence wherever it may lead. Our test is as simple as it is rigorous. By Atlas is somehow connected to this cluster of 7 comets. That connection would leave behind signatures that are observable. The test criteria: temporal correlations that exceed statistical probability, orbital relationships that suggest more than coincidence, and physical interactions that can be measured and verified. We are not looking for subtle hints or vague signs, patterns that require creative interpretation. We are searching for concrete evidence that is quantifiable to convince the most skeptical of astronomers, the kind of data that turns speculation into scientific fact. The significance of the investigation, the importance of this investigation, goes far beyond academic curiosity. If these 7 comets arrived independently, governed by no laws, other than the cold mathematics of orbital mechanics and the random discoveries of survey telescopes, then we are witnessing a coincidence, a remarkable celestial body. The universe is vast enough to surprise us from time to time, with a convergence that seems meaningful, but in reality is not. However, if there were some external influence, whether electromagnetic or gravitational, or something we have yet to consider, that guided these objects toward a synchronized convergence, then we are looking at evidence of forces at play on a scale that we can barely comprehend, forces that could reshape our understanding of how objects move through space. The core question invites us to consider the implications, because comets cannot simply converge by chance without a reason. In a solar system governed by laws that are predictable according to the laws of physics, each orbit tells a story. Each path carries the fingerprints of the forces that shaped it. If something has guided these objects onto their current paths, then those fingerprints must be detectable. This interstellar visitor adds another layer of mystery. Comet Atlas carries ice and dust forged in the fires of a distant star, tempered by radiation on a journey that perhaps lasted millions of years. Its chemical composition holds the clues of planets and other solar systems. Its behavior as it approached our sun revealed how materials from elsewhere react to heat. What if its arrival was not as random? What if the same force capable of shepherding 7 comets from the Oort cloud also guided an interstellar visitor to our solar system at just the right time? The questions multiplied like fractals, each answer giving rise to new puzzles. How could we possibly detect such an influence? What mechanism could operate across such vast cosmic distances to coordinate these bodies with such precision? And if that coordination were possible, what would that say about the true nature of our corner of the universe? As we prepare to examine each member of this group of 7 unusual comets, remember, the universe rarely reveals its secrets easily. Every discovery begins with an observation that doesn't quite fit the expected pattern. Every breakthrough begins with someone asking the question, why are things not as simple as they seem? The swarm of comets arrives, and with it come questions that could challenge everything about how our solar system operates. But first we need to meet our 7 visitors carefully and understand what makes each one unique. Coincidence or connection? The evidence awaits, and it is time to begin the measurements. Part 2. A roll call of the squadron. Let us meet our 7 visitors individually, because each one carries a story of discovery and its own cosmic journey. Think of this as a case where each suspect has an alibi, but somehow they are all present at the scene of the crime. Pan Star takes center stage as our first and brightest performer, discovered by the Panoramic Survey Telescope and Rapid Response System, a sky patrol based in Hawaii that has revolutionized the hunt for comets. This object promises to reach naked-eye visibility for observers in the Northern Hemisphere. The time frame extends from late March to May 2025, giving us months to study its path. What makes Pan-STARRS particularly fascinating is not just its potential for brightness, but also its orbital geometry. The comet's path brings it relatively close to the orbital plane of the Earth, making it easily visible from populated areas. For minds that search for patterns, this accessibility seemed too convenient, perhaps too convenient, for something that was supposed to have wandered in from the distant reaches of the Oort cloud, entirely by chance. Swan presents a completely different discovery story. The Solar Wind Anisotropy spacecraft, designed to study streams of solar particles, accidentally became a comet hunter when its hydrogen detectors began to pick up the light, characteristic of a cometary atmosphere. Swan comets often appeared suddenly in the data. Their hydrogen emission signaled their presence before optical telescopes could catch up. This hydrogen signature tells us something important about Swan's activity level. Unlike dormant rocks that only light up when the sun's heat awakens them, Comet Swan was already outgassing when it was discovered. It had been active for months, perhaps even years, creating the characteristic hydrogen shell that gave away its location. For a comet, supposedly following a random orbit, it seemed remarkably well prepared for its inner solar system debut. Stereo, perhaps provides the most impressive story of discovery. The solar observing spacecraft were positioned to monitor the activity of our star and caught this comet hurtling towards the sun. In their peripheral vision, the comets often become suicidal sun grazers, plunging so close to our star that they either collide with it, or disintegrate spectacularly, or emerge fundamentally changed by the experience. The timing here is noteworthy. Stereo's window of observation coincided with a period of increased solar activity, when our star's magnetic field was particularly turbulent. Was it a coincidence? Or is there something about the solar maximum that creates conditions which attract objects from the outer solar system? The correlation is too perfect to be ignored entirely. Atlas Quinn. Atlas brought with it the great expectations of the astronomical community, and its disappointment. When the Atlas Asteroid Impact Warning System first detected this object, initial brightness predictions suggested that it could become one of the most spectacular comets. Reality, as is often the case, was less impressive. Comet Atlas Kilo 1 would likely require binoculars or a small telescope for a comfortable viewing. But this is what caused Atlas to fracture. One became suspicious in our investigation, its discovery date, placing it squarely within the timeline of the swarm. However, its orbital characteristics suggest it has followed this path for thousands of years. Why would we find it now? Why this year? When 6 other objects crowded into the same observation window. Atlas Hetris, Atlas GBA, shares its survey origin with its sibling, K1, discovered by the same Hawaiian telescope system that has become extremely effective at finding potentially hazardous objects. The Atlas survey, operating as a cosmic early warning system, scans the entire observable sky every few nights, looking for anything that moves against the background stars. What puzzles careful observers is just how many recent comet discoveries have all originated from the Atlas survey. Not because the system is flawed, quite the opposite. Atlas represents advanced detection technology for asteroids and comets, but when the same survey system detects multiple members of an unusual swarm, patterns begin to emerge that demand an explanation. Lemon, Comet Lemon, brings another lineage to our cosmic gathering. The Catalina Sky Survey on Mount Lemmon in Arizona has been hunting for objects since the 1990s, accumulating one of the most comprehensive databases of small celestial bodies in the solar system ever compiled. Lemmon's discoveries carry the prestige of decades of observation and careful orbital determination. Expectations for Lemmon's appearance remained modest, perhaps an object visible with binoculars, at best. But its position in our procession is precisely what makes it interesting. Lemon appears in the middle of the pack, neither leading the way nor bringing up the rear. It is positioned like a placeholder, maintaining the formation with mathematical precision, seeming unlikely to arise from orbital mechanics, purely by chance. Neat. Completes our set of 7 with a touch of historical irony. The Near-Earth Asteroid Tracking Program ceased operations in 2007, but the comets discovered during its active years continue to arrive right on schedule, following orbits calculated decades ago. Neat represents the legacy of the sky surveys, conducted systematically, proof that patient observation eventually yields results. What makes Neat's participation as it enters our swarm what is particularly noteworthy is the time lag between detection and arrival. This comet has been tracked for over 15 years, its orbit refined through thousands of observations. There is no uncertainty about its path, and no surprises about its timing. It is certain to arrive in 2025. The question is, why is it arriving with 6 companions? When we plot all 7 orbits on a single timeline, the convergence becomes undeniable. These are not objects discovered in 2025, appearing by chance. These are comets discovered in different years, by different surveys, using different methods of detection, all converging on the same narrow window of time. The diversity of their discovery circumstances makes the temporal coincidence all the more remarkable. Hero emissions, solar observations, asteroid surveys, and dedicated comet hunts have all contributed different pieces to this puzzle. It is as if the universe deliberately scattered the clues across multiple methods of detection to ensure their final revelation. We notice a statistically improbable pattern. Consider the statistical improbability. Comet discoveries follow a distribution that is nearly random, with occasional clusters rarely exceeding 2 or 3 objects. 7 comets arriving together within a few months is a statistical outlier that demands an explanation, and yet here they are. Each one follows an orbit calculated with precision that only gravitational mechanics could allow. Without error, with no room for creative interpretation, these paths were set millions of years ago, when our 7 visitors began their long journey inward toward the inner solar system. The question that haunts every careful observer is simple. What set these paths in motion with a coordination that is so apparent? What force acting across the distances and timescales of the vast outer solar system could nudge 7 different bodies toward synchronized arrivals? We are not claiming there is coordination. We are noting the pattern that makes such coordination worthy of investigation. Because while each individual comet follows perfectly natural laws of motion, their collective behavior suggests something more than mere chance. But before we can assess any connection with our interstellar visitor, we need to understand why this clustering strikes experienced astronomers as truly unusual. And that requires looking at what is normal, what a typical year for comets looks like. Part 3. Why is this unusual? Step into any observatory in a typical year and ask about the visible comets. The astronomer would likely sigh, check their database, and tell you about a faint object that requires a good telescope and dark skies. Perhaps, if you are lucky, there might be a comet visible with binoculars that dedicated enthusiasts are tracking. Most years go by without a single comet visible to the naked eye. This is the basic reality of comet watching: patience, disappointment, and the occasional rewards that require serious equipment to appreciate. The public remains completely unaware of the faint smudges that excite amateur astronomers. Comets, for most people, exist only in history books and disaster movies. But 2025 breaks this rule with the subtlety of a cosmic sledgehammer. 7 noteworthy comets will appear just months apart, many of them bright enough to be captured with a regular camera, a few reaching binocular visibility, and at least one promises to be a spectacular naked eye show for the casual observer. The mathematics of comet discovery. To understand how truly unusual this concentration is, we need to consider the mathematics of comet detection and visibility. Modern sky surveys have revolutionized our ability to spot distant objects, but they have not changed the fundamental physics that determine when a comet becomes bright enough for us to notice. Modern survey systems, like the Panoramic Survey Telescope and Rapid Response System, operating from the Haleakala Observatory in Hawaii, scan the entire observable sky. Every few nights, the Catalina Sky Survey Program in Arizona covers different regions of the sky with systematic precision, and NEOWISE, the space-based infrared telescope, detecting the thermal signatures of objects invisible to instruments on the ground. These survey programs detect hundreds of comets and new asteroids each year. They remain forever observable only by telescope. Only a tiny fraction become bright enough to attract public attention. The statistical expectation. The statistical expectation for any given year is less than one object reaching naked eye brightness, with an additional 2 or 3 comets that are accessible to serious amateur astronomers. However, improved detection capabilities do not explain the unusual abundance of 2025. Survey telescopes find more objects, but the proportion that develop into notable comets remains consistent with historical patterns. Better instruments detect fainter objects farther away. They do not magically create bright comets where none existed before. The determining factors of brightness. The key is that visibility depends on intrinsic properties, which the surveys cannot change. Its brightness depends on its size, composition, and its distance from the sun at its closest approach. These characteristics were determined millions of years ago, when gravitational perturbations first nudged these objects toward the inner solar system. The findings of modern surveys simply announce arrivals that were already inevitable. We are not seeing more bright comets because we are searching more thoroughly. We are finding the bright comets that would have always arrived in 2025, regardless of our ability to detect them. A critical implication. This distinction holds tremendous significance for our investigation. If improvements in surveys explained the clustering, we would expect to see similar patterns in recent years as telescope technology has advanced. Instead, we see 2025 standing alone as an unusual cluster of activity. This suggests that our 7 comets are not merely a product of better detection. They represent a true physical clustering of objects, arriving from the distant reaches of the solar system within the same narrow window of time. And that brings us back to the central question. What could have caused this remarkable convergence? A reality check on brightness. This reality check on brightness deserves careful attention because the media often exaggerates otherwise modest objects into spectacular events, leaving casual observers disappointed. The magnitude scale works counterintuitively. Smaller numbers indicate brighter objects, represents the limit of naked eye visibility under a pristine dark sky. Most suburban observers need binoculars to see anything fainter than magnitude 4. Predicting the brightness of comets has considerable uncertainty, as the rate of outgassing depends on their composition and the heating from the sun in ways that are difficult to calculate precisely. The objects can brighten significantly if they contain volatile materials that vaporize suddenly, or they can be disappointing if the surface develops an insulating crust of dust, which suppresses activity. Despite these uncertainties, experienced comet observers develop a reliable intuition about which objects are worth watching. Solar activity and its impact. When veteran astronomers express surprise at the packed schedule of 2025, their reaction carries the weight of experience from observing objects in otherwise empty skies. The solar maximum adds another layer of complexity to our unusual year. The sun operates on an 11-year cycle, alternating between quiet periods with few sunspots and phases of pronounced activity by frequent solar flares and coronal mass ejections. The year 2025 coincides with the solar maximum, when the star's magnetic field reaches its peak turbulence. Solar storms can significantly affect the behavior of comets, creating spectacular disconnection events and unusual tail formations, making modest objects appear more active than their intrinsic brightness would suggest. The enhanced solar wind during the maximum period also amplifies a comet's ion tail, potentially making our 7 visitors appear more beautiful. A period of solar minimum. However, solar activity does not create comets, but only affects their appearance after they reach the inner solar system. The objects themselves were already destined for these encounters. In 2025, regardless of the sun's changing moods, an active solar maximum might make them more spectacular to observe. But it doesn't explain why 7 different comets would choose this particular year to make their debut in our solar system. Cognitive psychology and the tendency for pattern recognition. This is where human psychology enters the equation in ways that complicate objective analysis. Our brains evolved to detect patterns, even in random data, because missing patterns could actually be fatal in an ancestral environment. This pattern recognition ability serves us well in many contexts, but it can also lead us to perceive meaningful connections where none exist. Events that cluster together naturally capture our attention and demand explanation. When multiple rare events occur at the same time, we instinctively search for an underlying cause, rather than accepting a temporal coincidence. This cognitive bias becomes especially strong when the events seem coordinated or purposeful. A series of 7 precisely triggers this kind of pattern-seeking response. Because the objects appeared within a few months, it seemed too organized to be random. Our intuition about probability rebels against accepting such a cluster as mere random chance. However, rigorous statistical analysis shows that apparent clusters happen frequently in random distributions. Indeed, if you flip a coin long enough, you will find long streaks of heads or tails that might seem impossible, but are mathematically inevitable. The human mind finds it hard to accept these clusters as a natural product of randomness. The criteria for scientific analysis, the challenge for our investigation, is to separate the legitimate statistical anomalies from the kind of clustering to the pattern-seeking brain, but lies within normal variation. We need measurable criteria to determine when a pattern exceeds the bounds of reasonable coincidence. This is where careful orbital analysis becomes crucial. If our 7 comets share subtle gravitational influences, similar source regions, or synchronized perturbations that exceed statistical probability, then we have grounds to suspect there is external coordination. If their clustering merely represents a superficial pattern that emerges randomly from large datasets, then coincidence becomes the most plausible explanation. The standard for evidence must be set sufficiently high. Extraordinary claims require extraordinary evidence, and asserting that something has guided 7 comets to their coordinated appearances certainly qualifies as extraordinary. We need detectable signatures that can convince skeptical astronomers, who are accustomed to dismissing spurious correlations, potential physical mechanisms. As we prepare to consider the potential mechanisms for such coordination, it's worth remembering that the universe occasionally creates genuine surprises, challenging our assumptions about how things work. Sometimes the improbable turns out to be the correct explanation, and sometimes coincidences hide deeper truths, waiting for careful investigation to reveal them. The comets are real, their timing is unusual, and the questions demand answers. But what kind of force could coordinate objects over such vast distances and enormous timescales? And could our interstellar visitor, perhaps, provide the missing piece to this cosmic puzzle? Part 4. The Invisible Hand. When astronomers encounter patterns, they turn to 2 fundamental explanations: gravity and electromagnetism. These forces govern almost everything that moves in space, from planetary orbits to the behavior of charged particles in a comet's tail. If something is hurting the 7, comets toward their synchronized destinations. It must be acting through one of these mechanisms. To analyze the forces at play, let's start with gravity, as it is the undisputed master of the solar system's dance. Every object, any body with mass warps the spacetime around it, creating an invisible architecture that guides planetary orbits and the paths of comets. Gravity operates over infinite ranges with a precision that is mathematical, allowing astronomers to predict celestial events centuries in advance. But here's the crucial limitation. Gravity is extremely weak and requires enormous masses to produce an effect that is noticeable over interplanetary distances. The Sun, with its overwhelming gravitational dominance, shapes the orbits, and any kind of gravitational influence would be immediately apparent. To those calculating the orbits, studying these objects, mathematics is unforgiving. A comet's orbital elements, its inclination, its eccentricity, and its period reflect the gravitational forces it has experienced throughout its journey. These signatures cannot be hidden or disguised. If some massive object had steered our 7 visitors, its mark would be evident in their orbital characteristics, has demonstrated how gravity works in practice. The giant planet has created gaps in the asteroid belt, capturing families of Trojan asteroids that follow its orbit and redirecting countless comets through gravitational encounters. We can measure these effects precisely, calculate the forces involved, and predict future interactions with confidence. This gives us a template for detecting hidden objects. Analyzing electromagnetic forces. Electromagnetic effects offer a different possibility, but are similarly limited. Comets carry electric charges, as solar radiation ionizes their gas clouds, and these moving charges react to magnetic fields in measurable ways. The solar wind, a continuous stream of charged particles, flows out from our star and shapes a comet's ion tail, and can cause impressive disconnection events during magnetic storms. But electromagnetic forces act quite differently from gravity. They affect a comet's tail and atmospheric behavior. Without significantly altering, a comet's tail may twist and oscillate in response to solar magnetic field activity, but the comet itself continues to follow the orbit, determined by gravity with incredible precision. The idea that electromagnetic fields could control the coordinated arrival of 7 comets at a rendezvous point faces insurmountable physical problems. Such control would require magnetic field strengths far exceeding anything in the solar system, and the energy requirements would dwarf the output of our Sun. We are talking about forces that only exist in the immediate vicinity of neutrons, stars, and black holes. Detection criteria and data analysis. This brings us to the criteria for detection, distinguishing speculation from science. True manipulation, whether gravitational or electromagnetic, must leave observable evidence that withstands rigorous analysis. We need common orbital elements, pointing to a shared origin, consistent influences and perturbations that exceed measurement errors, synchronizations that are unexplainable by independent evolution. Let us apply these criteria to our 7 comets systematically, whether Pan-STARRS, Attu-RS, Swan, Stereo, Atlas G, another Atlas G, BA, Lemon, and Neat share common orbital characteristics, suggesting there are common influences, and that their 2 paths have been shaped by forces beyond the standard gravitational environment of the solar system. The preliminary answer is disappointing for conspiracy theorists, but reassuring for conventional physics. Each comet follows an orbit consistent with independent evolution under known gravitational influences. Their source regions, orbital inclinations, and temporal patterns show no evidence of coordination beyond the statistical clustering that can emerge from random processes. Pan-STARRS approaches from a different direction than ISON, and Stereo's sun-grazing orbit is unlike the more distant orbit of Atlas, kilometers. Lemon and Neat originated in different parts of the outer solar system and have followed very different paths to their current positions. The role of BA I Atlas as a potential coordinating factor. Our investigation takes an interesting turn when we consider BAI Atlas as a potential coordinator. Unlike the 7 traditional comets, is not bound by the laws of gravity that constrain the celestial bodies within the solar system. Its hyperbolic orbit and external origin make it a truly alien influence in our cosmic neighborhood. Could this one object, despite its small mass, possibly influence the timing or behavior of the traditional comets through mechanisms that we do not yet understand? This question pushes the boundaries of conventional physics, but it merits serious consideration. In this unusual context, the limitations of Atlas and the role of a shepherd are immediately apparent. Its estimated mass is far from a planetary scale, making its gravitational influence negligible. Its rapid movement through the solar system provides only a limited time for subtle perturbations to accumulate. Its orbit does not directly intersect with any of the 7 traditional comets, ruling out the possibility of a close approach that could produce measurable effects. However, the temporal coincidence remains unsettling for those who prefer their universe to be free of mysterious correlations. An interstellar visitor arrives during the year of greatest cometary activity in the recent history of the solar system. We feel it is too convenient to be a random coincidence. Even if Atlas cannot directly influence cometary orbits, could its presence somehow correlate with the conditions that make such a concentration more likely? The possibility of Atlas as an indicator rather than a cause. This question opens up a fascinating realm of speculation. While still adhering to observable limits, we are not proposing invisible tractor beams or exotic physics that violate established laws. We are asking whether the arrival of an interstellar object might coincide with processes that naturally increase cometary activity or detection rates. Perhaps Atlas serves as an indicator rather than a cause, a cosmic compass, pointing toward conditions favorable for comet discovery. Perhaps interstellar visitors prefer to arrive during periods when the outer solar system experiences enhanced gravitational perturbations, which increases the rate at which comets begin their sunward journeys. These possibilities require careful investigation, not casual speculation, but they illustrate how seemingly impossible coordination can emerge from natural processes operating at scales that we are only just beginning to understand. The universe has surprised us before, with subtle connections that at first seemed impossible as we prepare to meet our extraterrestrial suspect appropriately. Let's remember that the most profound discoveries often begin with observations that do not quite fit with conventional explanations. The impossible is simply waiting for better tools and more careful analysis to reveal its true nature. Part 5. The warning alarm that we are raising is not a blaring siren heralding the coming apocalypse, but the cautious tone of scientific curiosity faced with an unexplainable pattern. Think of it as a cosmic smoke detector, not a fire alarm. Something unusual is happening in our celestial neighborhood, and a responsible investigation requires us to consider it carefully before drawing any conclusions. The observation outlook for 2025. 2025 promises to bring a performance in the sky, turning ordinary stargazers into professional comet hunters. Many of the bright objects developed into spectacular displays, creating photographic opportunities that may come only once in a generation. Social media was filled with time-lapse videos of these celestial visitors gliding past the stars with an almost choreographed precision. The spectacle itself posed no danger. Comets are fundamentally fragile objects, loose collections of ice and dust, and organic compounds, barely held together by their own feeble gravity, as sunlight transforms them into glorious spectacles, capturing the public's imagination. We are literally witnessing them disintegrate in slow motion shedding material that will never be reclaimed. Even the closest approaches of the 7 comets remained at a safe distance. By astronomical standards, the closest pass of Pan-stars went by safely, well beyond the lunar orbit. Swan and Stereo followed orbits that posed no threat to Earth or any other major planet. These were flyby events, not collision courses, the source of the alarm. The real alarm came from the pattern recognition systems that evolution has deeply ingrained in the human brain for the purpose of survival. When multiple unusual events occur together, we instinctively search for deeper causes rather than accepting random coincidence. This reaction greatly helped our ancestors in detecting coordinated threats in the natural environment. But modern humans apply this pattern-seeking tendency to cosmic events that operate on scales far beyond our intuitive understanding. We see 7 comets at once and immediately wonder who sent them. What force could coordinate such precision across vast cosmic distances? Why now? And why together? These questions become especially compelling when combined with the appearance of Atlas, an interstellar visitor whose timing seemed too coincidental to be mere chance. With social psychology and information amplification, the narrative almost wrote itself. An alien probe appears. A fleet of comets follows. Clearly, something is happening. Requires immediate attention. Social media algorithms amplify this narrative because the mystery and the potential for conspiracy theories generate the engagement metrics that drive the economy of the platforms. Videos suggesting hidden connections between celestial events receive more views than thorough explanations of mechanics, orbits, and statistical probability. The story grows with each retelling. Our shared desire for meaning in a universe that seems random. Our principle of responsibility becomes crucial. The principle of scientific accountability. Every bold claim must pass rigorous testing against established physics and observational data. Speculation is allowed, even encouraged, but it must be clearly labeled and adhered to, of appropriate evidence. Entertainment value does not justify promoting unfounded theories as factual conclusions. The distinction between spectacle and substance must be continually emphasized. Beautiful does not mean coordinated. Dramatic does not mean artificial. Impressive does not mean threatening. The universe often creates natural phenomena that exceed our aesthetic expectations, without the need for far-fetched explanations. The impact of solar activity on perception. Let's consider how the increased solar activity in 2025 will amplify the visual impact of the parade of our comets. The solar maximum brings frequent coronal mass ejections and high-speed particle streams, which can significantly affect the behavior of a comet's tail. The ion tail can stretch across many degrees of the sky during strong solar storms. Disconnection events can create the illusion of the comet shedding pieces on command. These effects will make for spectacular photographs and videos, making it seem as if there is coordinated behavior among our 7 visitors. They are just independent reactions to the same solar stimulus. In conclusion, the balance between wonder and science. 2025 will bring us one of the most spectacular natural displays in history, watching 7 comets together, creating a visual feast in the night sky. Their simultaneous appearance, amplified by the solar maximum, will create images and experiences that future generations will long remember. However, it is important that we approach this phenomenon with a balanced scientific eye, open enough to recognize the natural wonder, but also rigorous enough to distinguish between rational curiosity and unfounded speculation. The comet swarm of 2025 may be one of the most impressive statistical coincidences that we have ever witnessed, or it may hold deeper secrets about how the universe works. Whatever the final answer may be, to experience a truly special year for astronomy, a year when the night sky will remind us that we live in a universe full of wonders, still waiting to be discovered. Social media will be filled with images that seem to capture synchronized tail movements and other phenomena suggesting external control. The reality will be more mundane, but no less fascinating. Each comet reacts independently to the same solar environment, creating an apparent coordination through a shared exposure to heightened solar activity. It's like seeing 7 different weather vanes, all pointing in the same direction during a storm, reacting in sync to a common influence. Rather than evidence of centralized control, the timing of this solar maximum adds another layer to our investigation. Why did our 5 unusual comets coincide with peak solar activity? Is there a connection between the solar cycle and the rate at which comets begin their journey from the outer solar system? Could the gravitational or electromagnetic effects associated with the solar maximum influence the timing of comet appearances? Somehow, these questions venture into speculative territory, but they are still grounded in measurable phenomena. The sun's activity follows cycles that are well documented and correlate with various space weather effects. If the solar maximum somehow increases the likelihood of comet detection or appearance, then that correlation should be detectable in historical data spanning across multiple solar cycles. Framework. The investigation we are establishing requires vigilance, constant vigilance against confirmation bias, the tendency to interpret ambiguous evidence as supporting preferred conclusions. When we see unusual tail behavior, our first response should be to check for solar storm activity, not to invoke exotic coordination mechanisms. When bright outbursts occur, we should examine the comet's composition and solar heating, rather than assuming external agents. When the orbit presents anomalies, we should verify the precision of our measurements and consider known sources of interference before proposing unknown influences. This disciplined approach does not eliminate wonder or discourage legitimate speculation. It simply ensures our sense of mystery is calibrated to actual observations, not to wishful thinking. The universe already has enough real puzzles, without us needing to create additional, artificial ones. For this comet is an anomaly, a valid, statistical one worthy of serious attention. Such a concentration is rare enough to justify a careful investigation into its potential causes. If our analysis finds nothing, enhanced by improved survey capabilities, then that conclusion also provides valuable information for our understanding of the dynamics of the solar system. But if we discover true correlations, time-synchronized orbital relationships, anomalies that suggest common influences, then we have identified what could reshape our understanding of how the solar system operates. The appearance of 3I Atlas in this unusual year adds an element of the unexpected, turning a statistical curiosity into a mystery that is potentially more profound. These interstellar visitors arrive perhaps once every 10 millennia, making this moment truly more significant than merely interesting. We are not asserting that the 3I Atlas caused or coordinated with the 7 comets, but we do acknowledge that this coincidence deserves investigation rather than being casually dismissed. Even without a direct causal relationship, the correlation could reveal indirect connections, shedding light on previously hidden aspects of the solar system's behavior. Our responsibility is not only to avoid raising false alarms, but also to ensure we do not miss genuine signals by being too quick to dismiss unfounded theories. The history of science is filled with countless examples of ideas that initially seemed ridiculous, but were eventually proven to be correct through a process of careful investigation and the accumulation of evidence. The challenge is to maintain appropriate skepticism while remaining open to evidence that may contradict conventional expectations. We need rigorous standards to evaluate extraordinary claims without becoming so rigid that we reject when it finally appears. As we prepare to examine our interstellar visitor in detail, let us remember the most profound discoveries often emerge from investigations that begin with simple questions about unusual patterns. Sometimes the universe is trying to teach us something new, and sometimes the lesson comes in the guise of a coincidence. The alarm has been sounded, and we are responding with the tools of scientific inquiry, not with a panic reflex. Whatever answers may await, they will emerge from meticulous measurement and analysis rather than speculation and assumption. But first, we need to understand our main suspect, the strange interstellar visitor whose appearance has raised so many questions. Part 6. The Interstellar Visitor, 3I Atlas, represents the third interstellar object, confirmed to pass through our solar system, a cosmic wanderer, formed around another star, and now making a flyby through our cosmic neighborhood, just once. Unlike all the other objects we have discussed, this visitor doesn't carry a local birth certificate. It is truly alien, in the most literal sense possible. The importance of this distinction cannot be overstated. Every comet in our 7-member flock originates from our solar system, within its gravitational embrace, formed from the primordial materials that built the planets and moons 4.5 billion years ago. But 3I Atlas carries ice and dust that condensed around another star in another stellar nursery, under conditions we can only imagine. Think of it as receiving a message in a bottle from a distant shore, except the bottle did not cross an ocean, but the vast distances between star systems. The journey had likely lasted for millions of years, during which time our visitor had drifted through the near-perfect vacuum of space between the stars, bombarded by cosmic rays, and slowly accumulated the chemical signatures of this great journey. Most importantly for our investigation, Atlas posed no collision threat to Earth. Its orbit carried it safely, past all the major planets, on a trajectory which would ultimately return it to interstellar space, never to return. This was a mission of precision, not an invasion, assuming, of course, that mission and invasion are relevant concepts for what might be merely a wandering, ancient block of ice. The comet-like behavior of Atlas added another layer of complexity to its story. Far from the sun, where temperatures should have kept its ice solidly frozen, the object had developed a detectable cloud of gas and a tail. Solar heat should not have been sufficient at that distance to drive that kind of outgassing, creating the visible activity of the comet. However, clear observations revealed a fuzzy appearance, a characteristic that distinguishes an active comet from an inert asteroid. This early activity suggested either an unusual composition, perhaps containing volatile substances that evaporate extremely quickly at very low temperatures, or some internal heat source driving the outgassing process. Regardless of solar heating, offered tantalizing clues about the conditions in the star system where this interstellar visitor originated. The scientific excitement surrounding any interstellar visitor stems from its unique status as a direct sample from another planetary system. In other words, the measurements we take, spectral analysis of its chemical composition, photometric monitoring of its brightness variations, astrometric tracking of its precise trajectory, all provide information about the processes of star formation, beyond the influence of our own sun. But our investigation was centered on a question that was entirely different. Could this interstellar visitor somehow be related to the unusual timing of our 7 comets? The correlation could simply be coincidental, but the risk is high enough to justify a careful investigation rather than a superficial dismissal. If there is a real connection between Biolus and our 7 traditional comets, it would manifest through observable signs and withstand rigorous analysis, temporal patterns that exceed statistical probability, orbital relationships that suggest more than mere coincidence, behavioral anomalies indicating shared influences rather than independent evolution. The absence of such signs would be strong evidence against any connection, leaving us with only an interesting coincidence, but one that is ultimately meaningless. However, the presence of clear correlations would open up profound questions about the forces at play on scale that we can barely comprehend. Consider the implications of discovering that an interstellar visitor could somehow influence the behavior of the native inhabitants of our solar system, would suggest mechanisms of interaction far beyond what current physics predicts, hinting at connections between star systems that transcend the simple gravitational relationships we currently understand, even without resorting to exotic physics. The temporal correlation between bias and our comet swarm deserves serious attention. Visiting interstellar objects are very rare, perhaps once per decade, based on current detection rates. Their visits should be randomly distributed over time, uncorrelated with events within the solar system. However, we have an interstellar visitor arriving in the year of the most unusual comets in recent memory. The probability calculation is very simple. If the interstellar arrival and the comet storm are independent events, their simultaneous occurrence should be correspondingly rare. The more unusual each event is, the more suspicious their coincidence becomes. Of course, correlation does not imply causation, and suspicious timing does not constitute proof of a connection, but it justifies the kind of detailed investigation that we are undertaking. If the universe is trying to teach us something about previously unknown relationships between interstellar objects and local objects, we need to listen carefully enough to hear the lesson. Brightness expectations for Bialis require careful management to avoid later disappointment. Unlike the spectacular members of the 7 comets in our flock, this interstellar visitor will mostly remain a telescopic object. Throughout its journey, its scientific importance far surpasses its visual impact. For casual observers, professional and amateur astronomers around the world are coordinating observation campaigns to maximize the scientific return from the brief visit of 2I Atlas. Every photon we collect from this object represents information that is irreplaceable about conditions in another star system. We will have no other chance to study this unique visitor. Its hyperbolic trajectory ensures only a single flyby, with no possibility of return. The observation campaign also offers the best opportunity for us to detect any connection between 2I Atlas and the flock of 7 comets. If shared anomalies exist, synchronized brightness, correlated changes in tail behavior, or a temporal relationship beyond coincidence, they will become apparent through monitoring, carefully observing all 8 objects at the same time. The challenge lies in distinguishing real correlations from the apparent patterns that emerge. When the human brain analyzes complex data sets, our pattern recognition systems evolve to detect meaningful relationships in noisy environments, sometimes identifying structures that do not exist, especially when we are eager to find connections. This is why our investigation maintains a separation, a strict one between observation and interpretation. When we measure changes in brightness, orbital elements, or spectral characteristics, those numbers represent objective reality. When we explore potential relationships between those measurements, we enter the realm of hypothesis testing, where skepticism must balance with curiosity. The scientific method provides the tools to navigate this balance. Statistical analysis can quantify the probability that observed correlations are the result of random chance rather than a true relationship. Independent verification ensures that apparent patterns persist under the scrutiny of multiple research groups using different instruments and techniques. But even the most rigorous analysis requires human judgment regarding what constitutes sufficient evidence for extraordinary claims. The assertion that the behavior of comets in the solar system is clearly linked to an interstellar object is an extraordinary one, requiring evidence robust enough to warrant serious consideration. As we prepare to examine the orbital characteristics of 3I Atlas and its predicted behavior, let us remember that the significance of this investigation extends far beyond resolving a strange coincidence. if genuine connections exist between these interstellar visitors, and the dynamics of the local solar system would fundamentally change our understanding of how the neighborhoods of different interact across the vast expanses of cosmic space, possibly interconnected more than our current theories suggest, with subtle influences operating on scales that dwarf mere statistical coincidence and challenge our ability to distinguish pattern from randomness. Whatever the case may be, the answer lies within the data, and it is time for us to examine our interstellar visitor more closely. The strange visitor has arrived, and its story is written, and is therefore geometric in its approach. Part 7. The Mysterious Orbit. The orbit of BAI Atlas reads like a cosmic passport, recording a journey that began in interstellar space, and will also end there, unlike elliptical orbits, which trap traditional planets and comets in endless cycles around the Sun. This visitor follows a hyperbolic orbit, the mathematical signature of an object, with enough velocity to escape the gravitational embrace of our solar system. Forever? Imagine a trajectory like a sweeping curve, speeding toward the Sun, from the depths of space, swinging around our star in a sharp curve, then accelerating back toward the interstellar darkness. There is no return, no second chance for observation. Atlas has only one pass through our neighborhood, and we are witnessing it in real time. The orbital elements tell a fascinating story about its origin and destination. The object approaches from a direction roughly corresponding to the constellation Perseus, although interstellar space has no signposts to mark its specific starting point. The hyperbolic excess velocity, the speed it maintains, even after escaping the Sun's gravitational pull, suggesting a journey lasting hundreds of thousands of years. From star systems, the nearest candidates. What is particularly fascinating about this orbit is its inclination relative to the ecliptic plane, the flat disk that contains the planetary orbits, and most of the debris in the solar system. BAI Atlas approaches at a moderate angle, rather than plunging in from high above or from far below the planetary plane. This near-ecliptic geometry means the object travels relatively close to the orbits, where the 7 comets in our swarm spend their time. This angle of inclination deserves careful attention, as it affects the probability of gravitational interactions with objects in the solar system. A visitor arriving from a high galactic latitude would sweep through our planetary system with minimal opportunity to influence local dynamics, but BAI Atlas has a more moderate inclination, keeping it within the general vicinity of the planetary orbits and comets for an extended period. This does not mean that close encounters are occurring. The distances involved are still measured in astronomical units, far beyond the reach of direct gravitational influence. But it does mean that BAI Atlas spends many months moving through the same region, common space, where our 7 traditional comets are making their own solar approaches. The retrograde nature of the 3 Atlas adds another layer of geometric complexity. While most objects in the solar system orbit the Sun in the same direction that the planets do, our interstellar visitor approaches from the opposite direction. This retrograde motion creates a relative velocity far exceeding any that the solar system naturally experiences during typical gravitational encounters. A high relative velocity usually minimizes the effects of gravity, as fast-moving objects spend less time within the zone of each other's gravitational influence. Somehow, it were to affect the traditional cometary orbits, the retrograde motion would actually work against that interaction by reducing the time of any potential encounter. These orbital characteristics establish important constraints for our investigation into any influence that Atlas might exert on the 7 comets must operate through mechanisms that do not require close proximity or a long period. The herding directly via conventional celestial mechanics seems increasingly unlikely when we consider the geometric details, but geometry alone does not rule out all possibilities of a connection. The temporal correlations between 3 events, Bialis, and the anomalous behavior in our 7 comets may reveal that transcend simple gravitational calculations. Let us consider the significance of the orbital nodes, where the orbit of Bialis intersects with the ecliptic plane. These intersections represent moments of approach closest to the central region that traditional comets and their dust trails occupy. If any interaction between interstellar objects and local bodies were to occur, these nodal crossings provide the most likely opportunities. The ascending and descending nodes of Bialis, which occur on specific dates, can be calculated with astronomical precision. If these dates correlate with the anomalous activity within our cluster of 7 comets, such as brightness outbursts, tail anomalies, or orbital perturbations, such a correlation would constitute solid evidence for some form of connection. The challenge lies in defining what constitutes anomalous activity in a context where the behavior of natural comets includes significant and unpredictable variability. Fluctuations in brightness and even minor changes in orbit occur regularly. As comets react to solar heating and outgassing forces, the bar for evidence must be set high enough to exclude normal cometary behaviors from consideration. Statistical analysis provides the tools to address this challenge objectively. If we continuously monitor the 7 comets, our traditional ones, and record all instances of brightness changes, tail events, or other notable behavior, we can test whether such events cluster around the dates of BAI Atlas's key orbital passages more than random chance would predict. The null hypothesis is that BAI Atlas and the 7 comets are unrelated, predicts that anomalous events should be randomly distributed over time, uncorrelated with the orbital milestones of the interstellar visitor. If observations reveal a statistically significant clustering of anomalous events around the key moments in the orbit of B Atlas, we would have empirical evidence to support the hypothesis of a connection. Even if a strong statistical correlation were found, we would still face the difficult challenge of identifying the physical mechanism that could explain such a connection. Traditional gravitational forces operate according to the inverse square law of distance, becoming negligible at the distances that BI Atlas maintains from traditional comets. Electromagnetic interactions also fall off rapidly with distance and require significantly charged bodies, unlikely to be met by an interstellar body of ice and rock. The universe has repeatedly surprised us with phenomena that operate through more subtle mechanisms than simple theories predict. Perhaps the presence of an interstellar object influences the interplanetary magnetic field in ways that we do not yet fully understand. Perhaps the hyperbolic orbit creates subtle vibrations in the fabric of spacetime that our current instruments cannot yet directly detect, but to which sensitive comets can respond. Or perhaps the connection, if one exists, operates through channels of information rather than direct energy exchange, a kind of cosmic resonance that we are only just beginning to explore. In the context of large-scale quantum mechanics, these speculations push us into a scientific realm that is highly ambitious. But the history of astronomy has taught us that the universe is often stranger than our imagination and simpler than our most complex theories. The real answer may lie somewhere between these extremes, not so strange as to violate known physics, but subtle enough to elude detection. Until we know exactly what to look for, while we wait for observational data to accumulate from the global monitoring campaign, it is important to maintain a balance between being open and a healthy skepticism about extraordinary claims. Thus, many lessons in intellectual humility, and this one will likely be no exception. The story of Comet Atlas and its 7 companion comets is being written in real time, every night. Observations add another page to this cosmic story. Whether the ending will be a confirmation of a deep connection between these distant objects, or the dismissal of a fascinating coincidence, that is ultimately meaningless. The journey of discovery has enriched our understanding of how the universe works, on scales far beyond our everyday experience, reminded ourselves of one of the greatest joys, the sense of mystery when facing the unknown, and the deep satisfaction of applying reason and careful observation to illuminate the dark corners of reality. The universe still holds many mysteries to be discovered, and each question we answer seems to open up 10 new questions, each one promising intellectual adventures of its own. Part 7. Testing the hypothesis. Any significant deviation from a random distribution would support some form of connection, even if the mechanism remains unclear. However, we must also guard against selection bias, the tendency to focus on apparent correlations, while ignoring instances where the expected patterns do not appear. A rigorous investigation requires tracking all potentially relevant events, not just those that seem to support a preferred conclusion. Atlas provides another opportunity to test potential hypotheses about a connection. As the object approaches perihelion, solar heating will drive increased outgassing, which could trigger corresponding responses in other objects. If some form of communication or coordination mechanism exists, the predicted light curve for Atlas shows a gradual brightening as it nears the Sun, potentially punctuated by sudden outbursts. If volatile materials vaporize rapidly, or if its internal structure fractures under thermal stress, each of these events occurs at predictable times and locations along its orbit, were to somehow react to the activity of Atlas, would occur at times that correlate with the predicted brightening events of the interstellar visitor. The temporal correlation would be very close, the stronger the evidence of a true connection becomes, rather than a random coincidence. However, we must also consider the possibility that the apparent correlations are the result of common responses to common external influences, rather than direct interaction between the objects. Solar activity, interplanetary magnetic field variations, or other elements of space weather phenomena could affect all comets at once, creating a coordinated appearance without direct communication between the objects. This solar influence hypothesis predicts that any correlated behavior could be traced back to specific space weather events, solar flares, coronal mass ejections, or high-speed particle streams interacting with cometary atmospheres in measurable ways. The presence of such solar triggers would argue against exotic coordination mechanisms and in favor of conventional astrophysical processes. The orbital characteristics of Y4 Atlas also constrain the timing of any potential influence on objects within the solar system. The traveler's hyperbolic trajectory ensures a brief passage through our region, perhaps 18 months from its initial detection, until its final departure from view. This limited interaction time means that any influence on the 7-comet cluster must manifest relatively quickly and be detectable with current instruments. Subtle influences, accumulating over decades or centuries, would remain invisible during the brief duration of Comet Atlas's visit. As we consider the specific predictions for perihelion, remember that orbital mechanics operate with the precision of clockwork, regardless of the strange possibilities we are investigating. Comet Atlas will reach its point of closest approach to the Sun at a time and position determined by gravity, indifferent to human speculation about alien coordination or interstellar communication. The numbers do not lie, and the geometry tells its own story. But whether that story includes a connection to our 7-comet cluster remains an open question that perihelion may finally answer. Part 8. What happens at perihelion? Perihelion represents the moment of truth for any comet, the closest point of its approach, gradually accelerating into a crescendo of activity. For BA Ialis, this milestone is particularly significant, as it marks the moment an interstellar visitor experiences the full intensity of the radiation and particles emitted from our star. The physics of perihelion is both predictable and dramatic. As BA Ialis draws closer to the Sun, The solar energy and radiation intensify, according to the inverse square law, doubling in brightness and heat, with each halving of the distance. The ices, frozen solid during its long interstellar journey, creating a surrounding shroud of gas and dust, transforming a dark body into a bright, active comet. But the composition of interstellar ices may differ from the predominantly water-based mixture typical of comets in our solar system. Ba Aeolus was formed in the outer regions of another star system, where the temperature and chemical conditions might have favored different molecular species: carbon monoxide, carbon dioxide, methane, and more exotic compounds may dominate its composition. These compositional differences should be revealed through spectral analysis. During its passage through perihelion, each molecular species will produce characteristic emission lines, and excited by solar radiation, the spectrum of Ba Atlas will essentially serve as a chemical fingerprint of the environment, preserved across millions of years of interstellar travel. If our investigation has uncovered a true connection between Ba Atlas and the 7 comet swarms, perihelion offers the most likely time for spectacular revelations. The intense heating from the sun, driving the comet's peak activity, could also trigger any mechanisms that might coordinate behavior among the multiple bodies. The observational signs to watch for are both subtle and dramatic. A sudden increase in brightness often marks the vaporization of particularly volatile materials or the exposure of new icy surfaces as the protective dust crust erodes away. These outbursts can increase the comet's brightness by a factor of 10 hours or more within a few hours, creating spectacular opportunities for observation while providing clues about its internal structure and composition. The jets of material erupting from specific locations on Atlas's nucleus could create an asymmetrical thrust effect, slightly altering the comet's trajectory. These non-gravitational forces are a well-documented phenomenon in traditional comets, but their presence in an interstellar visitor would offer unprecedented insights into how materials from other star systems react to the influence of our Sun. The development of Comet Atlas's tail deserves special attention, as it offers a real-time display of the interaction between interstellar material and the solar wind. The ion tail forms when the Sun's ultraviolet radiation ionizes the comet's gases, creating charged particles that are pushed away from the Sun under the influence of the solar magnetic field. The behavior of this ion tail, its length, direction, and its response to variations in the solar wind, how gases from another star system interact with the particles emitted from our Sun. Any unusual characteristics compared to the tails of comets can often suggest differences in composition that help distinguish interstellar material from local materials. The dust tail follows different physical laws, shaped by radiation pressure instead of magnetic forces. The size, distribution, and composition of the dust particles will determine the degree to which solar radiation can deflect them from a ballistic trajectory, barely deviate from their original path, while microscopic particles can be pushed into long, sweeping, curved tails, stretching across the sky. If Comet Atlas were to produce a spectacularly unusual dust tail, it could indicate a composition of fine particles that react strongly to solar radiation pressure, or a fragmentation during its perihelion passage, which could suddenly release large amounts of previously trapped dust locked within the comet's internal structure. Breakup events are the most dramatic possible outcome that can occur during a perihelion passage. The combination of heat from the Sun, rotational stress, and internal pressure from vaporizing volatiles sometimes overcomes a comet's weak gravitational bonds, causing the object to break apart, sometimes splitting into multiple fragments that disperse along its orbit. For Atlas, fragmentation would be particularly significant because it will provide access to the interior materials that have remained pristine since the comet formed in another star system. The newly exposed surfaces from the fragmentation will offer unprecedented opportunities for spectroscopic analysis of the cometary materials, which are truly pristine. But the fragmentation could also complicate our investigation further into potential connections with a comet swarm. Multiple fragments following slightly different orbits could create the impression of coordinated behavior where none actually exists, simply through the geometric complexity of tracking multiple related objects. At the same time, the solar wind environment during the perihelion passage of Atlas adds another variable that could affect both the interstellar visitor and any potential connections with other comets. The period of solar maximum means enhanced particle densities, stronger magnetic fields, and coronal mass ejections are more frequent, which can strongly influence the behavior of the comet's tail. These space weather effects create spectacular sights, such as tail disconnection events, plasma instabilities, and magnetic reconnection events, can make the comet's tail appear twisted, kinked, or to detach completely. Such events occur independently in each comet's surrounding environment, but they respond to the same agent from the Sun, potentially creating an apparent coordination, even if there is no real coordination. The key to distinguish real coordination from a common response to solar conditions lies in the timing, precision, and geometric analysis. Solar wind disturbances propagate outward from the Sun at a speed that is predictable, arriving at different comet locations at times. If the unusual behavior in our 7 comets correlates with the events of BA Atlas, but cannot be explained by the time lag of the solar wind's propagation, then the correlation becomes significantly more interesting. Amateur astronomers around the world are preparing observation campaigns to monitor Comet Atlas throughout its passage through perihelion, providing distributed coverage that no single observatory can match. This citizen science network will generate continuous light curves, photographic documentation of the development of the tail, and real-time data alerting if there are any outbursts. A major outburst or fragmentation event occurred. The observational coordination extended to professional facilities with space telescopes, ground-based observatories, and specialized surveys hunting for comets, all contributing to the most comprehensive study of an interstellar visitor ever undertaken. Every photon of light we captured was scientific data, irreplaceable about the conditions in another star system. But our investigation required the parallel tracking of all 7 traditional comets during the same period, searching for behavioral anomalies that might correlate with the events of Borisov and Atlas. This comparative approach would help distinguish between normal cometary variability and possibly significant correlations exceeding statistical expectations. The necessary precision to detect subtle correlations pushed observational capabilities. Minor variations in brightness, slight asymmetries in the tail, or faint orbital perturbations might provide the only evidence of strange interactions operating below the threshold of conventional detection. As the comets approached perihelion, remember that the universe operates according to the laws of physics, always remains constant, regardless of our wishes for spectacular discoveries. Comet Atlas will brighten, develop a tail, and perhaps fragment, based on its own intrinsic properties, as it responds to the heat of the Sun, not according to any plan to bring forth revelations spectacular for observers on Earth. However, within those natural processes lie opportunities for profound discoveries about the nature of the material between the stars and its behavior in the solar environment. Whether those discoveries will include evidence of a connection to the swarm of comets of our 7 remains an open question that only careful observation can answer. The cosmic time machine continues its precise operation, unconcerned with speculation, but faithfully providing the data we need to distinguish between fanciful wishes and genuine revelation. Part 9. the comets swarm in the sun. Our sun operates in cycles, eclipsing human attention spans, alternating between periods of relative calm and phases of dramatic activity. With the regularity of a cosmic clock, the 11-year solar cycle, which governs this behavior, is peaking in 2025, transforming our star into a spectacular and more volatile version of its usual self. The solar maximum brings with it a multitude of sunspots, dark patches that mark areas where powerful magnetic fields pierce through the solar surface. These magnetic fields, which store immense amounts of concentrated energy, sometimes release it explosively, launching charged particles and electromagnetic radiation into space, traverse the solar system in a matter of hours or days. For our investigation of the 76 comets, this heightened solar activity presents both opportunities and challenges. The increased particle density and stronger magnetic fields of the solar maximum can significantly amplify the behavior of the comets, making otherwise unremarkable objects appear far more spectacular than they would otherwise. During quieter solar periods, consider how a coronal mass ejection, a billion-ton bubble of magnetized plasma erupting from the sun's corona, interacts with a comet's delicate ion tail. The shock wave and distorted magnetic fields can compress, twist, or break off completely the tail in events that unfold over many hours and create some of the most spectacular comet photographs possible. These tail disconnection events occur when the magnetic field, carried by the solar wind, undergoes an extremely rapid change that the comet's existing tail structure cannot adapt to. The old tail is left behind, drifting away like space debris, while a new tail begins to form in the reconfigured magnetic field. For observers unfamiliar with the physics of space weather, these events can look almost supernatural. A comet's tail can suddenly develop kinks, knots, or helical structures that seem to violate the simple physical laws of gas flowing out from a central source. The tail may appear to detach completely, creating the illusion that something has attacked or damaged the comet. In reality, these phenomena represent normal reactions to unusual solar conditions. The comet itself remains unaffected. Only its ionized gas tail reacts to the changing magnetic environment. But the visual impact can be so dramatic that observers inevitably searched for strange explanations rather than accepting space weather as the ordinary cause. This solar influence to our investigation, as all 8 objects in our study, the 7 traditional comets plus 3Y Atlas, all shared the same space weather environment. All of them experienced the same coronal mass ejection, the same high-speed particle stream, and the same magnetic field variations that characterize a solar maximum. If dramatic tail events occur simultaneously across multiple comets, the simplest explanation is a common reaction to common solar triggers, rather than a mysterious coordination among the objects themselves. A solar storm, a single large one, can affect the tails of comets throughout the entire inner solar system, creating a synchronization that has nothing to do with communication or coordination between the comets. The increased solar activity in 2025 also affects Earth's magnetosphere in ways that amplify the perceived drama. In our cometary investigation, geomagnetic storms caused by the impact of solar particles can disrupt satellite communications, interfere with GPS navigation, and even threaten power grid systems. In extreme cases, more visibly, these storms push the auroral zone to lower latitudes, allowing observers at mid-latitudes to witness the dancing lights, usually reserved for the polar regions. The combination of an active comet and an active aurora creates a spectacle, supernatural in its intensity and timing. But it is important to distinguish between causation and correlation. In these relationships, solar storms affect both the comet's tail and Earth's magnetosphere, but the comet does not cause the geomagnetic disturbance. The sun drives both of these phenomena independently, creating coincidental effects with overlapping timing, without implying any causal relationship between the comet and the effects on Earth. This distinction becomes important when evaluating claims about a link between Comet Atlas and various phenomena on Earth. If satellite systems fail or power grids experience issues during the interstellar object's passage, the sun's activity provides a much more plausible explanation, compared to the curious influence of a distant, small meteorite. The timing of the solar maximum coincided with the year of our unusual comet, raising interesting questions about the potential correlation between the solar cycle and the detection or appearance patterns of comets. Could increased solar activity somehow influence the rate at which comets begin their inward journeys from the outer solar system? Could the gravitational or electromagnetic effects associated with the solar maximum affect the timing of a comet's appearance? These questions delve into the realm of speculation, but they are rooted in phenomena that are measurable. The sun's activity follows well-documented cycles, which would leave detectable signatures in the statistics. If a true correlation exists, historical data spanning many solar cycles could reveal whether periods of high solar activity coincide with increased cometary activity more often than by random chance. Such an investigation would require carefully separating the solar effects from any potential link between Biela and our flock of 7 comets. When the unusual tail behavior occurred, our first response should include checking the space, weather monitoring systems for coronal mass ejections, high-speed solar wind streams, or other recorded solar phenomena as a triggering factor. Only after accounting for the known effects of the sun can we reasonably consider more exotic explanations for the phenomena we have observed. This methodological caution is not blind skepticism, but a recognition that the universe frequently produces spectacular displays through completely understandable natural processes. The investigation into the potential connection between Atlas and our 7 comets unfolds against the backdrop of a dynamic solar system, where the activity of the central star influences every object within its sphere of influence. Understanding this context is essential to distinguish between normal phenomena, amplified by unusual conditions, and any signs of coordination that might truly transcend conventional explanations. As we proceed with this investigation, let us remember that our sun is a variable star, powerful, capable of producing effects, dramatic throughout the entire solar system. Understanding these possibilities does not diminish the wonder of observing comets, but rather enriches it. It provides a framework for understanding the complex interactions between celestial bodies in space and the star around which we all orbit. The investigation into the potential link between Comet, Atlas, and the 7 traditional comets represents a unique scientific challenge. It requires a delicate balance between an openness to extraordinary possibilities and the rigor of ruling out conventional explanations. The data we gather in the coming months will not only illuminate the nature of this interstellar visitor, but will also test the limits of our scientific understanding of coordination and communication within the solar system. Whatever the final outcome may be, will enrich our understanding of the cosmos that we call home. Approach helps prevent hasty conclusions from arising from overlooking conventional causes in favor of sensational alternatives. Professional space weather monitoring systems provide real-time data on solar activity with the observed behavior of comets. The Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and ground-based magnetometer networks continuously monitor solar conditions and their propagation through interplanetary space. This monitoring infrastructure gives us an unprecedented ability to distinguish between cometary behavior driven by the sun and anomalous events, which could truly indicate other influences if by Atlas somehow affected the behavior of traditional comets Those influences should be detectable above the background noise of normal solar variability. Amateur observers contribute vital monitoring capabilities, supplementing professional space weather systems. Comet photographers worldwide document tail behavior, brightness changes, and structural changes with a temporal resolution, often exceeding the capabilities of professional observatories. Busy. This distributed observation network provides coverage continuous for the entire comet of hours, creating comprehensive datasets, enabling correlation analysis in detail between solar activity and cometary behavior. The more complete our observational record is, the more confidently we can identify truly anomalous events that require further investigation. Increased solar activity in 2025 ensures that our cometary investigation will take place against a backdrop of frequent space weather events. This active sun will create many opportunities for spectacular comet photography, while at the same time complicating efforts to identify subtle influences that might operate independently of solar drivers. The challenge lies in maintaining the standards appropriate for evidence while remaining open to genuine anomalies that could reveal previously unknown aspects of cometary behavior. The universe has surprised us before with subtle connections that at first seemed impossible, and the conditions of a solar maximum may provide the energetic environment needed to detect weak interaction effects. As our investigation prepares to examine how space weather affects conditions on Earth, remember that the sun's behavior is ultimately the primary cause of most of the dramatic phenomena that we associate with active cometary phases. The question is not whether solar activity influences cometary behavior, as that connection is well established, but whether there are additional influences operating alongside the solar effects in ways that current theory does not predict. The cosmic dance continues to be choreographed by the fields, magnetic fields, and particle streams that connect our star to every object within its gravitational embrace. But within that familiar dance, new steps may be waiting to be discovered. Part 10. Echoes on Earth. The influence of space weather on Earth creates a complex web of technological vulnerabilities that most people never consider until systems begin to fail unexpectedly. And although the comets themselves pose no direct threat to our planet, the enhanced solar activity that gives comets their spectacular tails can wreak havoc on the electronic infrastructure that modern civilization depends upon. Geomagnetic storms. Earth's response to the impact of solar particles can induce currents in power transmission lines, potentially overloading transformers and causing cascading blackouts. In March 1989, a storm brought down Quebec's power grid, demonstrating that space weather can have very real consequences for millions of people. Satellite systems face a more direct exposure to the bombardment of solar particles, accelerated high-energy protons and electrons, as solar storms can penetrate the shielding of spacecraft, causing temporary malfunctions or permanent damage to sensitive electronics. GPS navigation, satellite communications, and weather monitoring systems all become less reliable. During periods of intense solar activity, aviation faces an added layer of vulnerability, especially for flights over polar regions, where Earth's magnetic field offers less protection from cosmic radiation. Airlines frequently reroute flights during geomagnetic storms to prevent passengers and crew from being exposed to high levels of radiation, while also protecting the aircraft's electronics from the effects of space weather. These effects create a psychologically precarious environment for evaluating claims about a connection between celestial events and problems on Earth when the comet's activity peaks, coinciding with the solar maximum. The timing seems too convenient to be a coincidence. Power outages, communication failures, and navigational issues seem like evidence of a strange influence from our unusual comet. The reality is more mundane but no less fascinating, as solar storms affect both the comet's behavior and Earth's technological systems through entirely independent mechanisms. The comet reacts to the enhanced particle density and variations in the interplanetary magnetic field. Earth's infrastructure reacts to the same particle streams. As they interact with our planet's magnetosphere, a correlation exists, because both phenomena share a common solar cause, not because the comet is somehow influencing systems on Earth. This distinction is an important one to make. If satellite systems fail or power grids are disrupted during the interstellar object's passage, solar activity provides a much more plausible explanation than a direct influence from a small, distant celestial body. The temptation to connect dramatic timing with an exotic cause must be tempered, in favor of established physical mechanisms. Government agencies responsible for monitoring space weather have developed sophisticated warning systems. The sun, through their propagation across interplanetary space, to their impact on Earth's magnetosphere. The National Oceanic and Atmospheric Administration's Space Weather Prediction Center issues forecasts and warnings with the same level of urgency applied to severe terrestrial weather events. These monitoring systems allow for precise correlation between recorded space weather events and any technological problems that might coincide with unusual cometary activity. If infrastructure failures occur during periods of recorded geomagnetic storms, a solar cause becomes far more likely than a mysterious cometary influence. Heightened solar activity in 2025 ensures frequent opportunities for such correlations. Solar maximum conditions produce geomagnetic storms several times per month, creating numerous opportunities for temporal coincidences between infrastructure problems and comet sightings. The statistical expectation is that some correlations will occur purely by chance, regardless of any real causal relationship. Amateur radio operators provide an additional source of monitoring, who often detect space weather effects before official systems issue alerts. Radio wave propagation through Earth's ionosphere is significantly altered during geomagnetic storms, causing communication blackouts or unusual reflection patterns that experienced operators recognize immediately. This distributed sensor network provides real-world feedback on space weather conditions, which can help distinguish between solar-induced phenomena and potential anomalies that might suggest other influences. If the three eyes of Atlas were somehow affecting Earth's electromagnetic environment, those effects would be detectable through multiple monitoring systems. The investigative framework demands vigilance against attribution errors that arise when multiple dramatic events occur simultaneously. Human psychology strongly favors causal explanations for correlations in time, especially when the timing seems meaningful or purposeful. The more unusual the individual events, the more compelling their coincidence appears. But statistical analysis shows that apparent clusters occur frequently in truly random distributions. Flip a coin long enough and you will eventually see seemingly impossible streaks, but are mathematically unavoidable. And the same principle applies to the correlations between space weather events, cometary activity, and technological incidents. The challenge lies in developing objective criteria to distinguish between correlations that are meaningful and the kind of random groupings that emerge from complex systems. This requires establishing baseline expectations for how often different types of events should coincide by chance alone, and then testing the observed correlations against those statistical predictions. Professional space weather research has developed sophisticated tools to address these challenges. Superposed epoch analysis, cross-correlation functions, and other statistical techniques can quantify the strength of the relationship between different types of events, while accounting for the multiple comparison problems that arise when testing many potential correlations simultaneously. These analytical methods provide a framework for evaluating claims about connections between BA astronomical phenomena and terrestrial phenomena, without succumbing to the pattern-seeking biases that make coincidences appear more meaningful than they are. The standards of evidence must be kept high enough to avoid false alarms, while remaining sensitive enough to detect true signals if they exist. The global scale of modern technological infrastructure creates countless opportunities for apparent correlations between events in the sky and system failures, with millions of satellites, billions of electronic devices, and countless transmission systems operating continuously. A certain number of failures occur each day, for completely random reasons during periods of intense cometary activity or unusual solar behavior. These mundane incidents will be noticed and may be misattributed. A power outage that would normally be blamed on aging equipment or a maintenance issue might instead be blamed on the strange influence of a comet, if it happens to occur during a period of special astronomical interest. Education and clear communication become essential tools for preventing this misattribution. The more people understand the actual mechanisms by which space weather affects terrestrial systems, the less likely they are to invoke exotic explanations for phenomena that conventional physics already fully explains. This educational component extends to our own investigations of potential connections between BA celestial bodies, Atlas, and the 7 comet clusters, by maintaining a clear separation between established causal relationships and speculative possibilities. We can explore strange hypotheses without promoting unfounded theories into factual conclusions. The technological sophistication of modern civilization creates both opportunities and challenges in detecting subtle influences that might operate below the threshold of conventional space weather effects. Our increased sensitivity to electromagnetic phenomena may allow for the detection of weak signals that were immeasurable to previous generations. But it also creates more opportunities for correlations, spurious correlations, and misattributed causation. As we prepare to consider how human psychology and cultural narratives shape the way we interpret celestial events, remember that the universe operates according to physical laws that remain constant, regardless of our hopes for dramatic discoveries. Earth's response to space weather follows well-understood mechanisms, requiring no exotic explanations, even during periods of unusual cometary activity. The echoes of solar storms reverberate through our technological systems with effects that are predictable, measurable, analyzable, and attributable to their true origins. But within the noise of space weather, conventional, subtle signals may await detection by instruments sensitive enough to distinguish between correlation and causation. Our investigation proceeds grounded in established physics, but also alert to possibilities that might challenge our current understanding of how celestial and terrestrial phenomena interact. Across the vast scales of space and time, Part 11, Omens of Change. Throughout human history, bright comets have served as cosmic messengers, which cultures interpreted according to their deepest fears and highest aspirations. The appearance of multiple comets at once taps into psychological patterns that have influenced human behavior for millennia, transforming objective astronomical events into subjective narratives of destiny, change, and cosmic significance. Ancient Chinese astronomers maintained meticulous records about the appearance of comets, linking celestial events with dynastic changes, natural disasters, and social upheaval. Historical records from the Han Dynasty describe comets as celestial brooms sweeping away the old order to make way for the new, a metaphor showing that civilizations have always sought meaning in cosmic moments. Medieval European chroniclers interpreted the appearance of comets as divine warnings of impending disasters or momentous events. The Great Comet of 1066, appearing just before the Norman conquest of England, became forever linked with the fall of the Saxon dynasty and the transformation of English society. Whether the comet actually influenced events or merely provided a convenient symbol remains a matter of debate. Such correlations are deeply ingrained in historical memory. The 1758 return of Halley's Comet coincided with the 7 Years' War, a global conflict that reshaped political boundaries on 3 continents. American colonial observers saw the comet as an omen of independence from British rule, while European astronomers celebrated it as a confirmation of Newton's theories of gravitation. The same celestial event supported entirely different narratives depending on cultural context and political aspirations. These historical examples illustrate how the human mind naturally links unusual events into coherent narratives that are more meaningful than random coincidence. When multiple dramatic phenomena occur simultaneously, be it a comet, a war, a pandemic, or social upheaval, we instinctively search for underlying connections rather than accepting independent causes. This tendency to find patterns becomes particularly pronounced during times of social stress or uncertainty, when populations actively seek signs about the future's direction. The 2022 comet arrives in an era of rapid technological change, climate anxiety, and geopolitical tensions, creating fertile ground for interpreting celestial events as omens of transformation. The modern media ecosystem amplifies these ancient psychological patterns through mechanisms that medieval chroniclers would find astonishing. Social media algorithms prioritize engaging content over factual accuracy, ensuring that dramatic comet videos and speculative theories spread faster than careful astronomical explanations. The neural pathways that once helped humans detect real patterns in the natural environment now respond to digital stimuli, designed to capture and hold attention. Video editing software allows amateur content creators to produce compelling narratives that combine real comet footage with evocative music, dramatic narration, and carefully selected visual effects. These productions can achieve professional production values while promoting theories that would never pass peer review in scientific journals. The democratization of content creation means that anyone with internet access can contribute to the evolving narratives about celestial events. Many independent creators often arrive at similar interpretations without coordinated effort, creating the appearance of widespread consensus on ideas that may lack a factual basis. This decentralized storytelling process can quickly turn simple observations of 7 comets appearing in 2025 into complex narratives about cosmic significance, alien visitations, or an impending catastrophe. Each retelling adds new details, connections, and interpretations that gradually diverge from verifiable facts and drift toward pure speculation. The presence of the three-eyed atlas in this storytelling environment creates particularly fertile ground for creative interpretation. An interstellar visitor arriving at the same time as 5 of our most unusual comets provides precisely the kind of mysterious timing that the human brain interprets as intentional rather than coincidental. The story practically writes itself. An alien probe coordinates with a swarm of comets to send a message or a warning to Earth. The narrative satisfies multiple psychological needs at once. It provides an explanation for the unusual timing, assigns agency to seemingly random events, and positions observers as witnesses to significant history-making events. Professional astronomy faces growing challenges in competing with these compelling narratives for public attention. Careful explanations of orbital mechanics and statistical probability cannot match the emotional appeal of stories that turn observers into participants in dramatic cosmic events. Scientific uncertainty, when presented honestly, as a range of possibilities rather than definitive conclusions, can sound less credible than confident assertions about hidden meanings. The responsibility to maintain factual accuracy in this environment requires constant vigilance against the temptation to sensationalize scientific conclusions or to downplay genuine uncertainties when we acknowledge that some correlations exceed statistical expectations. While stressing that correlation does not prove causation, we risk our audience tuning out in favor of sources that offer more definitive answers. However, this challenge also presents opportunities for education that traditional astronomy outreach rarely achieves. The high level of public interest in our 7 comets. The investigation creates teachable moments about testing, hypotheses, statistical analysis, and the distinction between evidence and interpretation. By maintaining a transparent separation between established facts and speculative possibilities, we can model the scientific process while exploring ideas that push against conventional boundaries. The investigation becomes an exercise in critical thinking, demonstrating how extraordinary claims require extraordinary evidence without dismissing unusual observations, simply because they seem unlikely. The cultural lenses through which people interpret our findings will inevitably shape observers' conclusions, often unswayed no matter what evidence we present. Those seeking confirmation of extraterrestrial visitation will interpret ambiguous results in favor of their preferred hypotheses. Conversely, skeptics committed to conventional explanations will dismiss even strong correlations, deeming them insufficient evidence for exotic mechanisms. This polarization reflects deeper questions of epistemology, how we decide what constitutes reliable knowledge, and sufficient evidence to accept extraordinary claims. Different communities apply different standards based on their training experiences and their philosophical commitments about the nature of reality. The scientific approach requires a provisional acceptance of conclusions based on available evidence, while remaining open to revision in light of new data. This intellectual humility can look like weakness compared to the confident certainty that characterizes both true believers and dedicated skeptics. However, this flexibility represents science's greatest strength in distinguishing between genuine discoveries and wishful thinking. The history of astronomy includes countless examples of ideas that initially sounded absurd but were eventually proven correct through the accumulation of evidence, as well as compelling theories that ultimately failed when tested against more precise observations. Our investigation into the potential connections between the Biolas and the 7 comet swarms must navigate these cultural and psychological currents without being swept away. The evidence will speak for itself, but only if we maintain appropriate standards for its interpretation, while remaining sensitive to signals that might challenge conventional assumptions. As we prepare to examine the most sensational aspects of the public speculation surrounding our comet investigation, let us remember that the human fascination with cosmic mysteries reflects a legitimate curiosity about our place in the universe. The challenge lies in channeling that wonder into questions that can be answered through careful observation and analysis. The ancient observers who saw omens in the tails of comets were not entirely wrong. Celestial events do indeed provide information about cosmic processes that affect human civilization. But the connection operates through physics, not magic, and understanding them requires more sophisticated tools, intuition, and the telling of the omens that have arrived, carrying messages written in the universal language of mechanics, orbits, and spectra. But first we need to decode the more colorful human interpretations that will inevitably surround such mysterious times. Part 12. The Alien Hypothesis. The most sensational interpretation of our fleet of 7 comets requires the courage to state plainly: BAI Atlas is an artificial probe from another civilization, and the traditional comets represent a coordinated fleet responding to its arrival. This hypothesis pushes far beyond conventional astronomy into the territory of speculation, demanding extraordinary evidence. But the implications are so profound that dismissing it without investigation would also be unscientific. Let's consider what an artificial origin would actually look like through the lens of established physics, rather than science fiction. An engineered object traveling between star systems would need to solve problems that challenge our current technology. propulsion to cross interstellar distances, precision navigation over millions of years, and communication across light years of space. The energy requirements alone beggar human comprehension. To accelerate a small probe to the velocities necessary for interstellar travel requires energy sources far greater than current human capabilities. Nuclear pulse propulsion, antimatter engines, or exotic physics that we have yet to discover would be needed to achieve the speeds to get objects between stars in a reasonable amount of time. Navigation also poses similarly difficult challenges. The trajectory of BAI Atlas demonstrates incredible precision in targeting our solar system from a launch point potentially hundreds of light years away. Such accuracy would require detailed knowledge of stellar positions and their movements across vast geological timescales, suggesting observational capabilities and computational resources far beyond our own. But these engineering challenges, however impressive, do not violate the known laws of physics. Advanced civilizations could plausibly develop the technologies to solve the problems of interstellar travel. Why? Through the application of raw physical force, according to principles we understand but cannot yet implement. The question is not whether such probes are theoretically feasible or not, but rather whether BI Atlas exhibits the characteristics that distinguish an artificial object from a natural one. Spectroscopic analysis and detecting an artificial origin. Spectroscopic analysis provides the most direct tool for detecting artificial components. Natural comets show characteristic emission lines of water ice, carbon compounds, and simple molecules formed easily in the cold outer regions of star systems. Artificial probes might contain manufactured materials, such as refined metals, exotic alloys, or synthetic compounds that do not naturally occur in the environment where comets form. The spectrum of BI Atlas, when analyzed in sufficient detail, would indicate whether its composition matches the expectations for natural cometary material or includes signs suggesting an artificial origin. Any discovery of clearly fabricated substances would constitute compelling evidence for engineered construction, while a completely natural spectrum would be strong evidence against the artificial origin hypothesis. Behavioral analysis presents another avenue for detecting artificial characteristics. Natural comets follow ballistic trajectories, determined entirely by gravity and occasionally outgassing, which creates small but measurable thrust effects. An artificial probe might exhibit course corrections, attitude adjustments, or other maneuvers indicating active control, rather than a passive response to environmental forces. The orbital elements of BI Atlas show no evidence of non-gravitational perturbations beyond what natural outgassing could produce. Its trajectory seems consistent with a passive object, obeying physics rather than engineering. However, subtle control inputs could still be below the current threshold of detection, especially if designed to mimic the natural behavior of a comet. Communication signals and the coordination hypothesis. Communication signals are perhaps the most conclusive evidence for an artificial origin. Active probes would likely maintain contact with their creators through radio signals, laser pulses, or other electromagnetic signals that could be detected by telescopes. Terrestrial radio. The search for extraterrestrial intelligence community has protocols to analyze such signals and distinguish artificial from natural radio sources. Systematic monitoring of BAI Atlas across multiple frequency bands has detected no clear artificial signals, although the analysis continues as the object approaches closer to Earth. The absence of detectable signals does not rule out the possibility of an artificial origin, as advanced civilizations might use communication methods that we have not yet conceived of or frequencies that we do not monitor. The coordination hypothesis extends the speculation of an artificial origin to our 7 traditional comets, suggesting they represent a form of engineered formation to respond to the arrival of BAI Atlas. This scenario requires even more extraordinary assumptions about advanced technology and strategic planning across interstellar distances. Each member of our comet swarm would need independent propulsion and navigation capabilities, sophisticated enough to coordinate their arrival times within narrow windows. The logistics of such coordination staggers the human imagination. 7 different objects launched from potentially different locations, at different times, all arriving within a few months of each other, after journeys lasting millennia. However, the orbital characteristics of our 7 traditional comets show clear signs of originating within the solar system. Their composition aligns with expected models for objects formed in our outer system. Their discovery histories stem from well-documented survey programs, which have tracked these objects for years or decades. Their trajectories show no evidence of artificial course correction or coordinated maneuvers. If these objects were to represent artificial constructs, they would need to be extremely sophisticated camouflage operations, designed to perfectly mimic comets native to the solar system. Such a deception would require detailed knowledge of our astronomical capabilities and expectations, suggesting surveillance and analytical capabilities far beyond what they are displaying. Technologically, and in an overall assessment of the alien hypothesis, the temporal correlation between BAI Atlas and our comet swarm remains the strongest argument for some form of coordination, even if the mechanism remains unclear. Statistical analysis of comet appearance patterns could reveal whether 2025 is a truly unusual clustering, exceeding reasonable expectations for a random distribution. But the timing alone provides weak evidence for artificial coordination when considered in the context of increasing survey capabilities and the natural variability in comet detection. The rise of automated sky surveys significantly increases the likelihood of detecting objects that might have gone undetected in previous decades. The psychological appeal of extraterrestrial explanations reflects deeper human needs to find purpose and intelligence behind seemingly random events. When faced with anomalies and coincidences, we naturally prefer explanations involving agency rather than accepting that randomness creates patterns that appear meaningful but actually are not. The alien hypothesis also soothes existential anxieties about humanity's cosmic isolation and technological limitations. If advanced civilizations are visiting our solar system, it suggests that we are not alone in the universe and that technological development far beyond our current capabilities is possible. However, extraordinary claims require extraordinary evidence, and the alien hypothesis clearly qualifies as extraordinary. The burden of proof lies with its proponents to demonstrate that artificial features survive skeptical analysis, rather than requiring skeptics to prove a negative regarding the non-detection of sophisticated signals. Current observational data provides insufficient evidence to support a conclusion of an artificial origin for either BAI Atlas or any member of our comet swarm, although we cannot rule out definitively sophisticated cloaking activities that perfectly mimic natural objects. Such scenarios require assumptions about alien capabilities and motives, planets far beyond the available evidence. The investigation continues, as improved observations may reveal features that current analysis has missed. Closer approaches would allow for more detailed spectral analysis, higher resolution imaging, and more sensitive searches for artificial signals or anomalies in behavior. Professional astronomy maintains a healthy skepticism regarding exotic explanations, while continuing systematic observation and analysis, in order to detect genuine artificial features should they exist. The scientific method provides the frameworks to distinguish between wishful thinking and legitimate discoveries when applied rigorously. The search for extraterrestrial intelligence represents one of the most profound questions facing human civilization. If evidence were to emerge showing that Atlas, or any related object, exhibits genuinely artificial characteristics, that discovery would change our understanding of our place in the cosmos. But the rigorous standards required to convince skeptical scientists means the alien hypothesis remains in the category of conjecture rather than established fact. The wonder and possibility remain alive, while acknowledging that current observations favor conventional explanations over exotic alternatives. As we consider even more dramatic scenarios that human imagination has constructed around the unusual disturbance of this year, remember that maintaining scientific rigor does not require abandoning curiosity about possibilities that challenge conventional assumptions. The universe has surprised us before, with phenomena that at first seemed impossible. Part 13. The Doomsday Scenario. The darkest interpretation of the convergence of 7 comets paints 2025 as a year of civilization-threatening catastrophe, orchestrated by forces beyond human control. This apocalyptic narrative transforms celestial mechanics into cosmic warfare, turning ice and rock into weapons capable of ending human history. While such scenarios make for compelling fiction, evaluating them requires an honest consideration of reality, the risks versus the psychological fear associated with unusual astronomical events. In the analysis of actual impact risks, the true collision hazards follow well-understood physics, allowing for precise calculations of impact probabilities and consequences. When asteroids or comets approach Earth on orbits that could intersect our planet's path, professional astronomers can make predictions with mathematical precision. The orbital mechanics governing these calculations operate with absolute precision, leaving no room for ambiguity about the true risk of collision. None of the 7 comets has an orbit that poses any impact threat to Earth during their current approach: Atlas, Cuba, Luneos, and need all maintain a safe distance measured in millions of kilometers. Their closest approaches are also far outside the zone of gravitational influence that could lead to catastrophic collisions. Comet Atlas follows a hyperbolic orbit, carrying it safely past all major bodies in the solar system. Its interstellar origin and high velocity actually reduce the probability of collision rather than increasing it, as gravitational capture becomes impossible for objects moving at hyperbolic speeds. The absence of an impact risk does not eliminate all potential hazards associated with enhanced cometary activity. Space weather and technological risks. The effects of space weather caused by the sun during solar maximum can threaten technological infrastructure in ways that modern civilization is struggling to adapt to. Power grids, satellite communication systems, and navigation networks all face vulnerabilities during periods of intense bombardment by solar particles. But these technological risks stem from solar activity, not from the behavior of comets. Our star's 11-year magnetic cycle reaches its maximum intensity in 2025, independent of any cometary appearances. The temporal correlation between active comets and active solar conditions reflects a response common to the dynamics of the solar system, not a causal link. From comets to solar behavior. Statistical risk assessment. Quantifying risk requires statistical analysis, separating real threats from the kind of random clusters that feel meaningful to the human brain, which loves to find patterns when many low-probability events occur. At the same time, intuitive risk assessment often overestimates the likelihood that something coordinated and threatening is happening. Professional risk analysis uses a mathematical framework to account for the multivariate comparison issues inherent in evaluating many potential correlations. At the same time, as happens when examining many possible relationships between different types of events, some apparent patterns will emerge purely by chance, regardless of any real causal mechanism. Doomsday scenarios gain psychological traction by grouping our 7 comet clouds plus 3 eye-atlases into a single threatening entity, rather than treating each object as an independent phenomenon. This combination turns 7 separate low-risk events into one seemingly high-risk situation, seemingly demanding immediate attention and preparation. However, orbital mechanics does not recognize such an artificial grouping, as each object follows its own trajectory, determined by gravitational forces acting independently on each comet. The apparent coordination exists in human perception, not in physical reality, created by the timing of observation rather than any real interaction between the objects. Historical precedents and correlational analysis. Historical precedents provide perspective on how unusual astronomical events relate to earthly disasters. Bright comets have appeared during periods of war, epidemics, and famine, and social upheaval throughout recorded history. But thorough analysis shows no statistical correlation between the appearance of comets and an increased rate of human disasters. This perceived correlation arises because dramatic astronomical events receive heightened attention during times when populations are already stressed by terrestrial problems. Chronicles written during difficult times naturally emphasize any unusual phenomena that seem related to the ongoing struggles, while similar astronomical events occurring in peaceful times attract less historical attention. Real risks and resource allocation. Modern civilization faces legitimate existential risks that deserve serious consideration, such as nuclear war, climate change, pandemics, and technological disruption. All pose real threats to human well-being. These risks operate through well-understood mechanisms that can be analyzed, modeled, and potentially mitigated through appropriate policies and preparation. The scenario of a doomsday comet distracts attention from these real risks by focusing anxiety on phenomena that pose a minimal actual threat to human civilization. The misallocation of limited attention and resources to imaginary threats reduces our collective ability to address the real challenges that demand sustained effort and coordination. In assessing evidence and applying professional scrutiny, sensational claims about cosmic threats must meet higher standards of evidence than casual speculation about unusual coincidences. When someone suggests that our comet swarm poses a civilization-level risk, we need specific mechanisms, quantified probabilities, and independently verifiable evidence, rather than vague assertions about suspicious timing. The scientific method provides a framework to evaluate such claims objectively. Hypothesis testing, statistical analysis, and peer review help distinguish between legitimate, evidence-based concerns and unfounded fears. Fear may reflect psychological bias rather than a physical threat, while emergency preparedness agencies maintain sophisticated monitoring systems to track actual space weather hazards and assess their potential impacts on critical infrastructure. These systems would detect and warn of any real threat posed by enhanced cometary activity or solar maximum conditions long before such threats could materialize. The absence of official warnings from the agencies responsible for monitoring space weather strongly indicates that scenarios predicting an imminent technological collapse due to comet-related phenomena are incorrect. Professional risk assessment experts have access to comprehensive observational data. Most importantly, there is no evidence of extraordinary threats that demand an emergency response. Educating the public about the actual risks of space weather helps maintain a proper perspective on the difference between a dramatic event and a true hazard. The reality of the threats is that solar storms can indeed threaten technological systems, but the threat operates through well-understood mechanisms that are predictable and can be monitored and mitigated through engineering solutions. The activity of Comet 2025 will provide spectacular observation opportunities and valuable scientific data on solar system dynamics. These benefits far outweigh any actual risks associated with the observation itself. The real danger lies in letting unfounded fears obscure scientific curiosity and legitimate educational opportunities. Responsible science communication requires a frank acknowledgement of uncertainties, while at the same time maintaining perspective on the magnitude of real risks, distinguishing between what is unexplained and what is alarming, as we acknowledge that some aspects of our investigation of our comets remain unexplained. We must also emphasize that unexplained does not mean alarming. The universe frequently presents phenomena that challenge our current understanding, without posing immediate dangers to human civilization. Scientific progress depends on systematically investigating such phenomena, while avoiding premature conclusions based on insufficient evidence or psychological biases. Part 14. The Disguised Invasion. The most sophisticated conspiracy theory. As we prepare to examine the most sophisticated conspiracy theories that human creativity has constructed around our 5 unusual comets, remember that extraordinary claims about cosmic threats require extraordinary evidence to justify serious consideration. The most sophisticated conspiracy theory surrounding our 7-comet phenomenon posits that we are witnessing the early stages of a disguised alien invasion. The astronomical events in this scenario, BAI Atlas serves as a command ship coordinating a fleet of objects disguised as traditional comets while precisely executing and preparing for the final occupation of our solar system. The technical challenges of this invasion hypothesis's camouflage would require a technological sophistication that the human imagination can scarcely conceive. Each alleged probe would need camouflage capabilities advanced enough to perfectly mimic a spectral signature. Modern spectroscopy can identify molecular species with extraordinary precision, distinguishing between isotopic ratios, revealing formation environments and chemical processes. Any artificial probe would need to carry materials that precisely match the expected composition for objects formed in our outer solar system billions of years ago. 2. Natural cometary outgassing behavior develops their characteristic appearance through the sublimation of volatile materials under the influence of solar heating. This process depends on internal structure, composition, and thermal properties developed over geological time. An artificial imitation would demand sophisticated engineering to reproduce these behaviors convincingly. 3. Light curves. The patterns of brightness variation characteristic of a comet's behavior provide another avenue for detecting an artificial origin. Natural comets typically exhibit smooth brightness changes, punctuated by occasional outbursts. Rotation periods are revealed through changing brightness, reflecting the natural tumbling of objects with irregular shapes under minimal gravity. Regarding the challenge of orbital characteristics, if our 7 traditional comets represent structures that are artificial, then their light curves would gradually reveal characteristics distinguishing engineered behavior from natural behavior. Artificially controlled rotation, precisely timed brightness changes, or other signs of active attitude control would become apparent through continuous photometric monitoring of the orbital characteristics of the camouflaged probes, posing the most fundamental camouflage challenge. Each member of our cometary swarm follows an orbit that can be traced back through millions of years of gravitational evolution. These orbital histories carry the imprints of their formation regions. Planetary encounters and gravitational perturbations have shaped their current trajectories. The logistics of an interstellar operation, creating artificial objects with orbital characteristics indistinguishable from those of natural objects within the solar system, would require launching them from appropriate distances and directions, while ensuring their orbits match those expected, for objects formed in specific regions of the outer solar system. The logistics of such an operation across interstellar distances and geological timescales defy comprehension. Then there is the historical evidence of their discovery. Furthermore, the discovery history of our 7 comets can be traced to well-documented survey programs that have tracked these objects for many years or decades. The Lemon and the Atlas surveys maintain comprehensive archives, recording the circumstances of each discovery and the subsequent orbital determinations to establish their expected arrival times. If these objects represented recently arrived artificial constructs, rather than long-period comets completing their natural orbits, their sudden appearance in survey data would have triggered immediate attention from astronomers experienced in orbital analysis. The absence of such alerts strongly suggests there is no scenario involving new artificial objects being deployed disguised as conventional comets. Then there is the communication challenge. The communication aspects of a coordinated invasion fleet would create additional opportunities for detection. Maintaining coordination among 7 dispersed objects, plus a command ship, would necessitate frequent data exchange via radio waves, laser communications, or other electronic signals, which ground-based monitoring systems could intercept. The search for extraterrestrial intelligence community operates sophisticated radio telescopes, continuously monitoring large portions of the sky for artificial signals. The Breakthrough Listen project, the legacy programs of the Arecibo Observatory, and numerous other initiatives maintain the search, systematically looking for precisely the kind of artificial signals that coordination among an invasion fleet would require. The questionable strategic logic. The strategic logic of camouflaging invasion scenarios faces fundamental questions about effectiveness, cost, and risk management. Why the camouflage? Why would advanced civilizations, capable of interstellar travel, opt for such elaborate deception, when a direct approach would achieve reconnaissance objectives more efficiently? What strategic advantage does camouflage offer when the target civilization lacks any defense against a technology capable of interstellar travel? The resource cost, the resource investment required to create and deploy 7 sophisticated camouflaged probes, plus a command ship, would exceed the total economic output of human civilization exponentially. Advanced civilizations capable of such an investment would possess such overwhelming technological advantages that deception becomes strategically irrelevant. Lack of evidence for hostile intent. Moreover, the invasion scenario assumes hostile intent, without any evidence of threatening behavior from any of the detected objects. None of the members of our cometary swarm have exhibited capabilities beyond what natural objects should possess. Biala's follows a departure trajectory that will carry it permanently out of the solar system, hardly consistent with establishing a presence. For long-term invasion purposes, the psychology behind conspiracy scenarios. The psychological appeal of invasion scenarios reflects contemporary anxieties about disruptive technology, resource competition, and the loss of human agency in the face of superior capabilities. These fears are readily projected onto anomalous astronomical phenomena, suggesting forces at work beyond human control or understanding. But speculation about alien intent, no matter how creative, cannot substitute for empirical evidence about the nature and behavior of the observed objects. Evidence-based conclusion. The burden of proof for the invasion hypothesis requires positive evidence of artificial characteristics, coordinated behavior, or threatening capabilities, rather than relying on an absence of evidence, demonstrating that the objects are entirely natural. Current observational data provides no support for the conclusion of an artificial origin. For any member of our comet swarm, spectral signatures indicate a composition consistent with natural formation within the solar system environment. Orbital characteristics match what is expected for objects undergoing gravitational evolution over millions of years. Behavioral patterns show no evidence of active or coordinated control beyond statistical coincidence. Scientifically, the burden of proof rests with those who advocate for extraordinary claims. To prove that artificial features exist through rigorous, skeptical analysis, The absence of such evidence does not prove that invasion scenarios are impossible, but it suggests that current observations favor conventional astronomical explanations over exotic hypotheses. Professional astronomers maintain systematic monitoring of all unusual objects, precisely to detect any features that might indicate an artificial origin. The scientific community considers such possibilities seriously enough to maintain established protocols for evaluating potential extraterrestrial artifacts, while applying appropriate standards of evidence to distinguish between speculation and legitimate discovery. The investigation continues. It continues as closer approaches allow for more detailed analysis of an object's characteristics and behavior. If true artificial signatures are present, they will become more apparent as observational capabilities improve and additional data accumulates over time. In conclusion, between science fiction and reality, the role of speculation. Science fiction scenarios play an important role in exploring possibilities and preparing conceptual frameworks for unexpected discoveries. But entertainment value does not justify promoting speculative scenarios as factual conclusions when the evidence is insufficient to support such extraordinary claims. The true mysteries of the cosmos. The universe provides enough real mysteries, without requiring us to invent additional puzzles based on wishful thinking, or the fear that leads to speculation. Our 7-star comet cluster represents a legitimate statistical phenomenon, worthy of investigation. But that investigation should follow the evidence rather than preconceived conclusions about invading fleets and cosmic conspiracies, a balance between openness and rigor as we prepare to synthesize our investigations, findings, and conclusions. Remember that maintaining scientific rigor does not require abandoning a sense of wonder about cosmic possibilities. The tools of empirical investigation that help distinguish between reality and illusion also provide the means to recognize genuine discoveries when extraordinary evidence finally emerges. The ultimate message is, the universe may yet surprise us with phenomena that challenge conventional assumptions, but such surprises will come through careful observation and analysis rather than speculative leaps far beyond the available evidence. Fear based on speculation serves no constructive purpose when detached from a rigorous analysis of probabilities and realistic mechanisms. Doomsday scenarios reveal more about human psychology than they do about cosmic physics. Our brains are inherently wired to find patterns, interpreting clustered unusual events as coordinated threats rather than random coincidences, especially during periods of social stress, when people are actively seeking explanations for their anxieties. The universe operates according to physical laws that are indifferent to human fears and expectations. Comets follow gravitational trajectories that can be precisely calculated. Solar activity follows magnetic cycles that can be statistically predicted, and space weather effects adhere to electromagnetic principles that can be measured and modeled. The cosmic machinery continues its precise operation, regardless of the dramatic narratives we construct around its most visible manifestations. Understanding that machinery provides both practical benefits and a profound satisfaction that transcends the temporary thrill of doomsday speculation. The conclusions of observers often remain unchanged regardless of the evidence we present. Those seeking confirmation of alien visitation will interpret ambiguous results in a way that supports their preferred hypotheses. Conversely, skeptics committed to conventional explanations will dismiss even strong correlations, viewing them as insufficient proof for exotic mechanisms. This polarization reflects deeper questions about epistemology, how we decide what constitutes reliable knowledge, and sufficient evidence to accept extraordinary claims. Different communities apply different standards based on their experience, training, and philosophical commitments about the nature of reality. The scientific approach requires a provisional acceptance of conclusions based on available evidence, while remaining open to revision when new data emerges. This intellectual humility might seem weak, compared to the confident certainty that characterizes both true believers and dedicated skeptics. Yet, this flexibility represents science's greatest strength in discriminating between genuine discoveries and wishful thinking. The history of astronomy includes countless examples of ideas that initially sounded preposterous, which were eventually proven correct through the accumulation of evidence, as well as compelling theories that ultimately failed when tested against more precise observations. Our investigation into the potential connections between Atlas and the 7 comet swarms must navigate these cultural and psychological currents without being swept away. The evidence will speak for itself, but only if we maintain the proper standards for interpretation, while remaining sensitive to signals that might challenge conventional assumptions. As we prepare to examine the more sensational aspects of public speculation about our comet investigation, let us remember that the human fascination with cosmic mysteries reflects a legitimate curiosity about our place in the universe. The challenge lies in channeling that wonder into questions that can be answered through careful observation and analysis. The ancient seekers of order who saw omens in the tails of comets were not entirely wrong. Celestial events do indeed provide information about the cosmic processes that affect human civilization, but the connection operates through physics, not magic, and understanding them requires tools more sophisticated than intuition and storytelling. The omens arrived carrying messages written in the universal language of mechanics, orbits, and spectra. But first, we need to decode the more colorful human interpretations that inevitably surround such mysterious times. Part 12. The Alien Hypothesis. The most sensational interpretation of our 7 comet flock requires the courage to state plainly, Atlas is an artificial probe from another civilization, and the traditional comets represent a coordinated fleet, reacting to its arrival. This hypothesis pushes far beyond conventional astronomy, into speculative territory that demands extraordinary evidence, but the implications are so profound that dismissing it without investigation would be equally unscientific. Let's consider what an artificial origin would actually look like through the lens of established physics, rather than science fiction. An engineered object traveling between star systems would need to solve problems that challenge our current technology: propulsion to cross interstellar distances, navigation with precision spanning millions of years, and communication across light years. The energy requirements alone are beyond human comprehension. To accelerate a small probe to the velocities needed for interstellar travel requires energy sources far greater than humanity's current capabilities: nuclear pulse propulsion, antimatter engines, or exotic physics we have yet to discover would be necessary to achieve speeds that carry objects between stars in a reasonable time frame. Navigation also presents equally daunting challenges. The trajectory of Atlas demonstrates incredible precision in targeting our solar system from a launch point potentially hundreds of light years away. Such accuracy would require detailed knowledge of stellar positions and their movements across vast geological timescales, suggesting observational capabilities and computational resources far beyond our own. But these engineering challenges, while impressive, do not violate known laws of physics. Advanced civilizations could plausibly develop the technologies, solving interstellar travel problems through the application of power, raw physics, following principles we understand but cannot yet implement. The question is not whether such probes are theoretically possible, but whether Atlas exhibits the characteristics that distinguish an artificial object from a natural object. Spectroscopic analysis and detecting artificial origins. Spectroscopic analysis provides the most direct tool for detecting artificial composition. Natural comets exhibit the characteristic emission lines of water ice, carbon compounds, and simple molecules that form readily in the cold outer regions of star systems. Artificial probes might contain manufactured materials, refined metals, exotic alloys, or synthetic compounds not naturally occurring in the comet-forming environment. The spectrum of Bay Atlas, when analyzed in sufficient detail, will reveal whether its composition matches the expectations for natural cometary material, or includes markers indicating an artificial origin. Any detection of substances that are clearly manufactured would constitute compelling evidence for engineered construction, whereas a purely natural spectrum would be strong evidence against the artificial origin hypothesis. Behavioral analysis offers another avenue for detecting artificial characteristics. Natural comets follow ballistic trajectories determined entirely by gravity, and occasional outgassing which produces small but measurable thrust effects. An artificial probe might exhibit course corrections, attitude adjustments, or other maneuvers that indicate active control rather than a passive response to environmental forces. The orbital elements of BAI Atlas show no evidence of non-gravitational perturbations beyond what natural outgassing could produce. Its trajectory appears consistent with a passive object obeying physics rather than engineering. However, subtle propulsion and control could remain below current detection thresholds, especially if designed to mimic natural cometary behavior. Communication signals and the coordination hypothesis. Communication signals are perhaps the most unambiguous evidence for an artificial origin, as active probes would likely maintain contact with their creators through signals, radio, laser pulses, or other electromagnetic signals that could be detected by ground-based radio telescopes. The search for extraterrestrial intelligence community has protocols for analyzing such signals and distinguishing artificial from natural radio sources. Systematic monitoring of BAI Atlas across multiple frequency bands has not detected any clear artificial signals, although the analysis continues as the object moves closer to Earth. The absence of detectable signals does not rule out the possibility of an artificial origin, as advanced civilizations might use communication methods that we have not yet conceived of, or frequencies that we do not monitor. The coordination hypothesis extends the speculation of an artificial origin to our 7 traditional comets, suggesting they represent a form of engineered formation. To respond to the arrival of BAI Atlas, this scenario requires even more extraordinary assumptions about advanced technology and strategic planning across interstellar distances. Each member of our cometary swarm would need independent propulsion and navigation capabilities, sophisticated enough to coordinate their arrival times within narrow windows. The logistics for such coordination stagger the human imagination. 7 different objects launched from potentially different locations, at different times, all arriving within a few months of each other, after journeys lasting millennia. However, the orbital characteristics of the 7 Chinye, our traditional comets, show clear signs of a solar system origin. Their compositions are consistent with models expected for objects formed in our outer system. Their detection histories stem from survey programs that are well documented and have tracked these objects for many years or decades. Their trajectories show no evidence of artificial course correction or coordinated maneuvers. If these objects were to represent artificial constructs, they would need to be camouflage operations of extreme sophistication designed to perfectly mimic natural solar system comets. Such a deception would require detailed knowledge of our astronomical capabilities and expectations, suggesting surveillance and analysis capabilities that surpass their apparent technology, an overall assessment of the extraterrestrial hypothesis. The temporal correlation between BANs, Atlas, and our comet swarm remain the strongest argument, in some form of coordination, even if the mechanism remains unclear. Statistical analysis of cometary appearance patterns could reveal whether 2025 represents a truly unusual concentration, exceeding reasonable expectations for a random distribution. But timing alone provides weak evidence for artificial coordination when considered. In the context of increasing survey capabilities and natural variations in comet detection, the rise of automated sky surveys significantly increases the likelihood of detecting objects that might have gone undetected in previous decades. The psychological appeal of extraterrestrial explanations reflects deeper human needs to find purpose and intelligence behind seemingly random events. When faced with anomalies, with coincidences, we naturally prefer explanations involving agency rather than accepting that randomness creates patterns that appear meaningful, but in reality are not. The alien hypothesis also soothes existential anxieties about humanity's cosmic isolation and technological limitations. For if advanced civilizations are visiting our solar system, it suggests we are not alone in the universe, and that technological development far beyond our current capabilities is possible. However, extraordinary claims require extraordinary evidence, and the alien hypothesis clearly qualifies as extraordinary. The burden of proof lies with its proponents to demonstrate that artificial features survive skeptical scrutiny, rather than requiring skeptics to prove negative propositions about the non-detection of subtle signals. Current observational data provides insufficient evidence to support a conclusion of artificial origin for either Atlas or any member of our comet swarm, although we cannot definitively rule out sophisticated cloaking activities that perfectly mimic natural objects. Such scenarios require assumptions about capabilities and alien motivations that go far beyond available evidence. The investigation remains ongoing as observations continue to improve, could reveal features that current analysis has missed, but a closer approach would allow for more detailed spectral analysis, higher resolution imaging, and a more sensitive search for artificial signals or anomalies in established astronomical behavior, maintaining appropriate skepticism about exotic explanations, while continuing systematic observation and analysis that could detect genuine artificial features, if they exist. The scientific method provides the frameworks to distinguish between wishful thinking and legitimate discoveries, when applied rigorously. The search for extraterrestrial intelligence represents one of the most profound questions facing human civilization. If evidence emerged showing that Comet Atlas, or any related object, exhibited truly artificial characteristics, that discovery would change our understanding of our place in the universe. But given the rigorous standards needed to convince skeptical scientists, the extraterrestrial hypothesis remains in the category of speculation rather than established fact. The wonder and possibility remain alive, while acknowledging that current observations support conventional explanations over exotic alternatives as we consider the scenarios, even more dramatic, that the human imagination has constructed around this unusual comet of the year. Remember that maintaining scientific rigor does not require abandoning curiosity about possibilities that challenge conventional assumptions. The universe has surprised us before with phenomena that initially seemed impossible. Part 13. Doomsday Scenarios. The darkest interpretation of the convergence of our 7 comets paints 2025 as a year of catastrophe, a threat to civilization orchestrated by forces beyond human control. This doomsday narrative transforms celestial mechanics into cosmic warfare, turning ice and rock into weapons, capable of ending human history. While such scenarios make for compelling fictional stories, their evaluation, they require an honest examination of the actual risks versus the fear, psychologically associated with unusual astronomical events. The analysis of actual impact risks, the real impact hazards, follow well-understood physics, allowing for precise calculations of impact probabilities and consequences when asteroids or comets approach Earth, on orbits that may cross our planet's path. Professional astronomers can predict and address these with mathematical precision, The orbital mechanics that govern these calculations operate with absolute precision, leaving no room for ambiguity about the true risk of a collision. Not one of our 7 comets has an orbit that poses any impact threat to Earth during their current approach. Pan-STARRS, SWAN, Studio, Atlas G1, Atlas G3, Launius, and Vanet all maintain safe distances, measured in millions of kilometers. Their closest approaches are also far outside the gravitational influence zone that could lead to catastrophic collisions. Comet Atlas follows a hyperbolic trajectory, carrying it safely past all major bodies in the solar system. Its interstellar origin and its high velocity relative to other objects actually reduce the probability of a collision rather than increasing it, because gravitational capture becomes impossible. For objects moving at hyperbolic speeds, the absence of an impact risk does not eliminate all potential hazards associated with cometary activity. Enhanced space weather and technological risks. The effects of space weather, caused by the Sun during its maximum conditions, can threaten technological infrastructure in ways that modern civilization is struggling to adapt to. Power grids, satellite communication systems, and navigation networks all face vulnerabilities during periods of intense bombardment by solar particles. But these technological risks originate from the Sun's activity, not the behavior of comets. The 11-year magnetic cycle of our star reaches its maximum intensity in 2025, independent of any cometary appearances. The temporal correlation between active comets and active solar conditions reflects a common response to the dynamics of the Sun, rather than a causal link from the comets to the Sun's behavior. In statistical risk assessment, quantifying risk requires a distinct statistical analysis to separate real threats from the kind of random clusters that feel meaningful to the human brain, which likes to find patterns when multiple low-probability events occur simultaneously. Intuitive risk assessment often overestimates the likelihood that something coordinated and threatening is happening. Professional risk analysis uses a mathematical framework to account for the problem of multiple comparisons, which is inherent in evaluating many potential correlations at once when examining many possible relationships between different types of events. Some apparent patterns will emerge purely by chance, regardless of any real causal mechanism. Doomsday scenarios gain psychological traction by lumping our 7 comets, plus the 3 Atlas comets, into a single threatening entity. Instead of viewing each object as an independent phenomenon, this combination transforms 7 separate low-risk events into one seemingly high-risk situation that appears to demand immediate attention and preparation. However, orbital mechanics does not recognize such an artificial grouping. Each object follows its own trajectory, determined by gravitational forces acting independently on each comet. The apparent coordination exists in human perception, not in physical reality, and is created by the timing of observation, rather than any real interaction between the objects. Historical precedent and correlation analysis. Historical precedent provides perspective on how unusual astronomical events relate to terrestrial disasters. Bright comets have appeared during periods of war, plagues, famines, and social upheaval throughout recorded history. But thorough analysis reveals no statistical correlation between the appearance of comets and an increased rate of human disasters. This perceived correlation arises because dramatic astronomical events receive heightened attention during times when populations are already stressed by terrestrial problems. Chronicles written during difficult times naturally emphasize any unusual phenomena that seem connected to the ongoing struggles, while similar astronomical events occurring in peaceful times attract less historical notice. Real risk and the allocation of civilizational resources. The modern world faces legitimate existential risks that deserve serious consideration: nuclear war, climate change, pandemics, and technological disruption all pose real threats to human well-being. These risks operate through mechanisms that are well understood, analyzable, and modelable, and are potentially mitigable through appropriate policies and preparation. The doomsday comet scenario distracts attention from these real risks by focusing apprehension on phenomena that pose a minimal actual threat to human civilization. The misallocation of limited attention and resources to imaginary threats diminishes our collective ability to address real challenges that require sustained effort, coordination, evidence assessment, and professional monitoring. Sensational claims about cosmic threats must meet standards of evidence higher than those for ordinary speculation about unusual coincidences. When someone suggests that our comet swarm poses a civilization-level risk, we need specific mechanisms, quantified probabilities, and independently verifiable evidence, rather than vague assertions about suspicious timing. The scientific method provides the framework for evaluating such claims objectively, where hypothesis testing, statistical analysis, and peer review help distinguish between legitimate, evidence-based concerns and unfounded fears. Fear reflects psychological biases rather than physical threats. Emergency preparedness agencies maintain sophisticated monitoring systems to track actual space weather hazards and assess their potential impact on critical infrastructure. These systems would detect and warn of any real threat posed by enhanced cometary activity or solar maximum conditions, long before such threats could materialize. The absence of official warnings from the agencies responsible for monitoring space weather strongly indicates that scenarios predicting imminent technological collapse are unfounded, due to comet-related phenomena are incorrect. As professional risk assessment experts, who have access to the most complete observational data, see no evidence of extraordinary threats that would require an emergency response. Educating the public about the actual risks of space weather helps maintain a proper perspective on the difference between a dramatic event and a real danger. Part 15. The message from the swarm after months of investigation. Tracking orbital mechanics, performing probabilistic statistical analysis, and examining every possible connection between the Atlas comets and our 7 comets. The evidence points to one conclusion. It is simultaneously reassuring and remarkable. We are witnessing a natural phenomenon that is extraordinary, rather than evidence of strange coordination or extraterrestrial intervention. The 7 comets of 2025 represent a genuine statistical cluster, attracting attention precisely because such groupings are rare enough to feel significant. Pan-stars, Swan, Stereo, Atlas C1, Atlas C4, Lonios, and Neowise are all following independent orbits, determined by the gravitational forces that began shaping their paths millions of years ago, long before human civilization existed to witness their eventual convergence. However, to dismiss this convergence as a mere random coincidence would be to diminish the profound beauty and scientific value of what we are experiencing. The universe has orchestrated a celestial festival, offering unprecedented opportunities for the comparative study of comets, public astronomy education, and a deeper understanding of the dynamics of the outer solar system. The timing may be natural, but its scientific and cultural impact remains extraordinary. The appearance of the interstellar visitor, Oumuamua, adds another layer of wonder as the first interstellar visitor ever recorded in our solar system. It clearly exhibited comet-like behavior. This object carried ice and dust forged around another star, tempered by millions of years of interstellar travel, now vaporizing under the light of our sun, to reveal tales of its extraterrestrial chemistry to telescopes around the world. The temporal correlation between our interstellar visitor and the 5 most active comets in recent memory continues to intrigue researchers, although the current evidence suggests more a random coincidence than causation, as the universe sometimes arranges emotionally meaningful patterns through entirely natural processes, reminding us that coincidence and meaning can coexist without needing mystical explanations. The results of the scientific investigation. The investigation revealed no unusual behavioral orbital relationships or temporal correlations beyond what statistical analysis would predict for independent objects influenced only by conventional gravity and solar thermal effects. Each comet tells its own story of formation in the outer solar system, the gravitational perturbations that initiated its current orbit, and its response to increasing solar radiation as it approaches perihelion. This conclusion does not diminish the scientific excitement surrounding the unusual celestial activity of 2025. Multiple bright comets offer a rare comparative opportunity within a single observing season. Researchers can study how different compositions, sizes, and orbital geometries respond to similar solar heating conditions, advancing our understanding of cometary physics in ways that individual observations cannot achieve. The heightened solar activity accompanying the solar maximum will amplify the visual spectacle of our cometary parade, while also providing natural experiments in space weather physics. Coronal mass ejections that threaten technological infrastructure create the dramatic tail disconnection and plasma instability events that make cometary imaging so compelling during active solar phases. In terms of community engagement and educational value, amateur astronomers worldwide are documenting this celestial festival in unprecedented detail, creating photographic archives that will inform scientific research for decades to come. The democratization of high-quality astrophotography means that hundreds of observers are contributing supplementary data to professional monitoring programs, multiplying our observational capabilities far beyond what any single institution could achieve. The public engagement generated by our investigation of the 7 comets shows how unusual astronomical events can foster interest in space science and critical thinking skills through the process of evaluating extraordinary claims based on available evidence, offering educational opportunities that traditional astronomy outreach activities rarely achieve. It shows how the scientific method distinguishes between speculation and established fact, future possibilities and the potential for discovery. The absence of strange connections does not rule out all possibilities for future discoveries. Continued monitoring might reveal subtle correlations that current analysis has missed, or closer approaches could allow for the detection of features that remain below the current observational threshold. And science progresses through incremental improvements in measurement, precision, and analytical techniques that occasionally unveil previously hidden phenomena. The statistical alignment characteristic of 2025 could also provide insight into the long-term dynamics of the solar system operating on timescales that exceed the human historical record. If similar alignments occurred in the past, or happen in predictable cycles, it might reflect gravitational resonances, the influence of solar cycles, or other periodic effects that shape the timing of comet appearances on astronomical scales. Professional astronomy will continue to observe and analyze, systematically, all unusual objects, maintaining vigilance for features that could indicate artificial origins or unusual physical processes. The community considers such possibilities seriously, while applying appropriate standards of evidence to distinguish between true anomalies and statistical fluctuations in complex datasets. Broader implications for science and society. The broader implications of our research extend beyond the specific question of a link between Pallas and the traditional cometary system. This process demonstrates how rigorous scientific inquiry can address unusual hypotheses without getting swept up in the speculation that such hypotheses generate in popular culture. Maintaining this balance between curiosity and skepticism is increasingly important, as social media algorithms amplify claims that are sensational faster than careful analysis can evaluate them. The scientific community has a responsibility to provide accurate information, while honestly acknowledging uncertainties rather than competing with entertainment content through exaggerated claims or hasty conclusions. The 2025 Comet experience also illustrates how the human psychology of pattern-seeking can transform objective astronomical events into subjective narratives about a meaningful cosmos. This transformation is not necessarily problematic. The search for meaning and wonder in celestial phenomena has inspired human cultures throughout history, but it requires a conscious separation between factual observations and interpretative frameworks. Modern tools and methods, the instruments of modern astronomy, provide an unprecedented ability to distinguish between genuine anomalies and apparent patterns that emerge from normal statistical fluctuations. These tools also reveal cosmic scale phenomena that surpass human imagination, without the need for exotic explanations, proving that reality often outstrips the creativity of speculation. As our investigation concludes, we are left with a universe that is at once more understandable and more mysterious than popular narratives suggest. The universe operates according to physical laws, which can be discovered and understood through careful observation. However, those very laws give rise to phenomena that challenge intuition and inspire continued exploration. The final message, the message of the 2025 swarm, ultimately, may be that the universe provides enough genuine wonder without requiring us to invent additional mysteries. 7 independent meteoroids converging through natural processes, while a single, first-of-its-kind interstellar object passes through our solar system, represents a cosmic coincidence worth celebrating for its remarkable timing. The educational value of this experience extends far beyond astronomy to the skills of critical thinking, applicable across all domains of human knowledge. Learning to distinguish between correlation and causation, evaluating claims based on appropriate standards of evidence, and maintaining curiosity while demanding rigor, provides intellectual tools that serve society well beyond the specific context of cometary investigations. Future observers may look back on 2025 as a turning point, the year when improved survey capabilities and social media attention combined to turn routine astronomical discoveries into phenomena, cultural events that captivated millions around the globe, into discussions about probabilistic evidence and the nature of scientific knowledge. The ultimate message of the swarm may be one of human curiosity and analytical capability, rather than the strange cosmic coordinations that represent the most remarkable aspects of this entire experience. We have developed tools sophisticated enough to detect interstellar visitors, calculate their trajectories with extraordinary precision, and evaluate extraordinary claims through rigorous statistical analysis. This technological and intellectual achievement deserves recognition, alongside any spectacular celestial phenomenon we are fortunate enough to witness. The universe may not send us messages through the coordinated appearance of comets, but it continues to offer opportunities for discovery, rewarding careful observation with a deeper understanding of our cosmic environment. The investigation concludes where it began, with awe at the unusual timing, a respect for rigorous analysis, and an appreciation for a universe that offers enough genuine mysteries to satisfy human curiosity. For millennia to come, hypotheses are tested, and evidence is evaluated, while the wonder is preserved intact for future investigations, waiting beyond our current observational horizon.